This summer school, I think we have no organizational remarks this time, so we jump right into the technical program. And it's my great pleasure to invite Josef or Joška Šivic from Czech CTU Prague and ELLIS Prague unit here for this tutorial. So Josef did his engineer or master's at the Czech Technical University in Prague. Then he did a PhD in Oxford. And then he spent quite considerable time in France in École Normale Supérieure, and now he's with the CIRC, which is the Czech Center for Artificial Intelligence, Robotics and Informatics, or something like that, at the Czech Technical University in Prague. They are actually our big friends and big competitors, because this is like a really good Czech IT and AI and robotics center. Josef was awarded like number of awards, but I think two of them are quite outstanding, because well, the people in Europe usually know the people out of Europe. We have these ERC grants that are really the very prestigious ones awarded by this European Research Council, and it's hard to get them, and you need to be good. And Josef actually has already a second one, so he had a junior or a starting one, and now he's working on this advanced ERC grant, which is really like quite an achievement, and there are not so many of them in Czechia and in Europe. So I think I stop here. I give him the floor, and thanks again, Joško, for being with us.
Thank you very much for the invitation. Yeah. It's really a pleasure to be here. I would like to maybe a little bit before I really jump into the presentation, I would like to get a little bit of the feeling what you know already. So who has heard of a transformer? Okay, so most, I think that's great, because I'm not going to explain it, so this is very important. And then some background, what you know about natural language processing. I guess transformer, but have you worked on NLP with language? Okay. With speech? Many people, that's great. Computer vision, images, videos, some people. Have you worked with a robot? Few people as well, not that many. Okay. So I think I got it roughly right, but I will try to in this presentation, it will kind of be motivated by the research which I do. So you will see lots of, some of our recent results, but I'll try to really go into a bit more detail. So especially I think I go into detail some of the computer vision stuff and then robotics, so that you get some more understanding. But it will be sort of really motivated by the sort of our recent research results. And the topic is learning for physical interactions, and what I mean by this is when we put cameras on robots and let them try to touch and interact with the world. And that's why I call it from pixels to machines that see, reason, and act. So my research area, really the background, is in computer vision. And so the purpose of the goal of computer vision is extracting information from images. Here is an example of a scene which is fairly complicated, but it's to illustrate that our human visual system is very good at this stuff. You can look at this image and understand what has probably happened. You can recognize the individual objects, the people, and not only this, but you can actually even imagine what would happen if you go and interact with the scene. That maybe, I don't know if from people in the background, in the back, if they see there is a ladder here. So you could probably imagine, you could climb this ladder and go up. So yet, I would argue that this level of understanding, we are not quite that with automatic computer vision, automatic visual understanding, although there's been a tremendous amount of progress in this area. And just to illustrate this problem, the input we'll be looking at are images, and there are the arrays of pixels. And the individual here, this would be individual pixel, and then if it's a black or like a grayscale image, this would be an intensity, or if it's a color image, it would be a RGB, like a 3 numbers for the color. And if it's a depth image, there will be a little bit of depth images. There are sensors which can measure also depth using different physical principles. I'll not go into this. That number might be actually a depth in centimeters, for example, at that particular location from the sensor. So these will be type of inputs. I think that I've covered what we'll be working with. And why I find this exciting, especially now, is that we can put a camera on robots, and many robots are equipped with visual sensors which provide an input measurement of the surrounding scene. So this is an example of the Atlas robot from Boston Dynamics. They have a more recent version which is completely electric. This one I think is still hydraulic. And the robot, you can see, it has a visual sensor. It's equipped with cameras, also these depth sensors. It sort of can measure the surrounding environment. And it has also actuators. It has these grippers, and it can grasp a particular object, and it can carry it and move it somewhere else. It can interact with the environment. And why it's interesting is that there is this sensor and the actuators. It's not only that the robot can plan the action and do something. What's even more exciting is that it can actually observe the outcome of its interaction and potentially learn from this interaction with the world. So the robot not only can go and grasp it, but it can say, have I grasped it correctly, or have I failed or succeeded in the interaction? So it's not about just the actions, but actually also closing the loop, learning from the outcomes of the interactions. I don't think we quite have really mastered this, even in the research community. Having robots can do interesting things, but we are not quite there that we have these continual learning robots which will be interacting with the environment and learning from these interactions. I also want to say, if you have any question, I'm here for you now for the next 3 or 4 hours. So if you have any question, don't hesitate to ask. Maybe someone else also has a similar question. So raise your hand and ask. Now, why is this interesting? Why would it be great if we have robots which could interact with the environment on the level, say, a human can? Well, first of all, it would be a revolution in manufacturing or repair. Imagine you really had these robots which could go around with similar skills, both perception and manipulation as humans. They could go manufacture stuff, they could repair things. These are examples of robots, sort of humanoid robots. This is like a model of an airplane, and so an airplane is an interesting example because actually it's not like you have in a factory where you manufacture 1,000 cars a day in exactly the same line. Every airplane is unique, so a lot of it is actually what's called small batch production, so it's done mostly by people who do it on demand, exactly what the customer wants. So the idea there is, at the moment, I think they have collaboration with Airbus, for example, is not that you would make a production line for airplanes. Actually, it will be more like the production line will be robots which would go inside and do the stuff to the specific order. The robot could go to places which are dangerous for people, or even if you have this mechanism of automatic understanding of the visual content, you could even give instructions to a novice human to do a particular task in the environment. And one more area, an example application. If we really did master this idea of having robots improving by themselves gradually over time, you could even imagine automating sort of surgical operations. There are at the moment robots which can perform surgical operations, but they are teleoperated by humans often. There is the famous Da Vinci one, for example. It's been happening for a while. At the moment, we've seen the most success using machine learning in medical domain and diagnosis. When we pool information from many experts, we can get to above human level performance with a machine, and this is in cancer diagnosis, breast cancer, which the algorithms can discover features which can detect the breast cancer years before it happens, because they sort of gather information over time and from many people. We don't have that in sort of the interaction with the patients in the surgical domain yet, but I think there is potentially a path towards that if we do master these techniques and we have robots which can actually learn from these interactions on a large scale. So these are just some examples of why this is interesting potentially. Instead, what we have now at the moment is, ChatGPT, as most of you have probably used it, or from Gemini. This is GPT-4, a little bit old now already. But these systems are in processing language sort of quite amazing. Yeah? So these systems, this is a slide from some of the sort of benchmarks, and the one which I find surprising, the first one is the uniform bar exam. So this is an exam with a lawyer, if you want to practice law in the US, you have to pass, and the GPT-4 system has, is passing it better than 90% of human. So these systems are very powerful in manipulating language, as most of you know. And at the moment, it seems that it's really due to combination of very powerful, learning algorithms, big models with lots of parameters, and sort of this parallelized training on supercomputers and lots of data. So this is from GPT-3. The training data I've listed here is 175 billion parameters, and training data is 300 billion words, which is about 2 million books. So the systems are trained on large amounts of data. So this is fantastic. So we have these systems which can work with text in an amazing manner. Yet we don't have a machine which would be at home and it can empty a dishwasher for us, which are sort of fairly basic tasks, or a machine which should have basic cooking skills as a 10-year-old. So my 10-year-old, almost, I wish she helped more in the kitchen, but she can do some of this stuff which robots can't at the moment. So why is that? Why we have these systems which can do amazing things with language, with text, yet we don't, they are not very good in manipulating the environment. So why this seems sort of intriguing? This observation is not new. This is something which is called Moravec's paradox. It's been already observed in the 80s by scientists like Hans-Peter Moravec, who is of Austrian origin, but has worked at CMU in the States. And in the 80s, he already made this observation. He wrote this, it's not a very thick book, but it's sort of full of interesting insights, which he sort of talks about this. And he says it's relatively easy to get computers to do intelligence tests or playing checkers. So that was, at the time, was kind of a capability, playing checkers, at an adult level. But when it comes to perception and mobility, it's difficult or impossible to give them the skills of a 1-year-old child. At the time, it was not even level on a 1-year-old child. Now it's better, of course, but we are still not on the level of human. So he had a hypothesis. We don't know. I don't think anyone knows at the moment why that is. He had a hypothesis, which is in the book, where he's saying is that the visual motor skills which we have in manipulating words are encoded in the sort of highly evolved sensory motor portions of the human brain, and have really billions of years experience. It has evolved from animals which had to move around the environment and sort of do things. Whereas the abstract thought is so in evolution, a relatively new trick. So what his intuition was that actually we humans, we are really Olympic athletes in this kind of interactive environment because it has evolved for such a long time, whereas the abstract thought, actually we are really amateurs. We are just haven't really, it's a very recent thing. So that's why the computers are kind of, easily better than this, because we are just not very good at the more abstract tasks. We are super good at these mobility tasks. So that was one hypothesis. We don't know if it's true, but we do have one observation, and it's that one of the enabling factors which we've seen for this amazing progress in language was training data. I mean, together coupled with the powerful training hardware and learning algorithms. But the training data was one of the key things. So now, by analogy, we are thinking, well, what if we get similar amount of training data for the robots, for the interaction with the environment? Maybe we will also start observing these sort of similar effects, emerging properties like we had in language. So at the moment, this is a sort of my classification, but I think it's sort of similar if you ask other people in the community. But at the moment, the community is on this quest of gathering the training data, using different things, different techniques, different directions, but with this vision that if we get enough of the training data of some form, we will be able to sort of see, we will see these sort of jumps in performance which we saw in language, and not just languages, in visual recognition as well. We saw the same thing with ImageNet and other things. We saw when we scaled the data, and probably, I'm not expert in audio, many of you are, is that, similar probably observed that if you scale training data sets, you also get better performance in audio, in speech. So maybe we'll also get it in the interaction. So I've classified this, and I will structure the rest of this lecture in these sort of 3 directions. The first one is learning from humans. The second one is learning from simulation of the real world. And the third one is learning from the other machines. And I will sort of show, as I said before, I will try to structure it around our work in this area, but also I will show work of others, sort of recent things which I find exciting. So it's a bit of a personal view of this area. And I'll try to cover some of, explain some of it, hopefully to the level that you will understand. But I will not sort of write down lots of equations here but I have links to papers which you can follow. Okay, so I will start with learning from humans. But one last thing, my intuition, of course, I don't know, no one knows, I think, but my intuition is that it's not going to be a single thing. That in the end, if we do reach success, it will be a combination. It will be a combination of these different factors. You will have some data from humans to pre-train, maybe some data from simulation for some things, and then finally, really the true scale, I think, as I will show you, I think will really come when we start learning, the machines start learning from each other. But, of course, I don't know, but I think it's going to be a combination. And second, in this sort of lecture, I don't know, I will see how far we get together, but I will try to sort of explain you some of the techniques which I think are important in sort of recent, I would say, in recent work, starting from a little bit of robotics, robot parameterization, trajectory optimization, object pose estimation, video language models, learning basic locomotion from simulation, so vehicle supervised versus supervised techniques. A little bit I'll talk about image generation, and also finally we end up with visual language action models, so the models which also generate motion. And I think Michal Hradič has explained some of it, so I think I know what he's explained, so I'll try to not cover that. I'm assuming you will know that. But if you see something which you don't know or something you've seen already, then raise your hand. I will try to go slower or faster. Okay, so first, as a motivator, so we are learning from humans at the moment. So there's been an area which I've been working on for a while, and I do think it's a very powerful one. To illustrate that, so this is an example of an instructional video. So here is a person, the person is explaining, so this is explaining how to change a car tire. In Czech Republic, we have to change car tires every 6 months, winter, summer. In case you don't know it and you happen to need to change because you have flat tire, you can actually, on your phone, you can Google up a video where someone is showing how to use the different tools to change the tire. And he's talking in language, explaining and showing how to use the tools. If you don't like the one particular video, actually you can find another one with different tools and different types of car. And in fact, there are really, I would say, thousands of different videos of different people showing how to change a car tire on YouTube. And in fact, there are really millions of different instructional videos in different domains, from car repair, cooking, gardening, or healthcare. But there are really, I would say, we did a data set which I think I will show. There's like tens of different thousands of domains or tasks and millions of videos. So we do treat it as a very nice test bed where we can sort of change, check how, benchmark or train different machine learning algorithms for understanding together visual information in video and natural language. Of course, ideally, we would like to have a machine which will just watch a video and be able to extract some kind of an instructional manual from that, some kind of abstraction, and then apply the same instruction manual to different environment that is to perform the task on the specific car. So that's of course the goal, but it's quite far at the moment. So I'll show you first just a little bit, like a few examples of steps towards reaching that goal. Here is an example of a first work a few years back. This is a YouTube video when someone is showing how to use a sledgehammer. And this is an extracted motion. So we just, from the single video, this is input, this is output, this is a trajectory of the person. So the trajectory would be the position of the different joints in 3D over time. But not only the person, but also the tool. The tool is modeled as a simple stick-like object. And the yellow arrows, which you see here, these are actually estimates of the interaction forces between the person and the ground, and the person and the tool. So, and this work I will not go too much detail. I'll show other work in more detail. I just want to show you that what kind of things are possible. We didn't manage to scale this up to very large scale because it was kind of, here you have to assume certain weight of to estimate the forces, certain weight of the objects or the people. But in overall, this type of pose estimation from video is using machine learning techniques. You can do it quite reliable at the moment, trained on lots of data. In addition to lots of data, we add the physical prior that we actually estimate the forces of the interaction. Now we say why you would want to do that. The reason is teaching robots. So here the intuition is, at the moment, if you have a robot like this, you have to program each motion manually. And programming the motion can be challenging, can take time, and if it's a dynamic motion, like using a shovel, it could be very difficult to just program it from a computer. So here, this is an example of work where we estimate the motion from the YouTube video and then transfer it on a robot. Yeah, so it's difficult because is this dynamic motion, and it's done by reconstructing the motion of the person and the tool from the video. Then we actually forget the person, only use the motion of the tool, and use it to initialize the motion in the simulated environment, and then sort of compute the robot motion in order to approximate the motion of the tool. So, but it's possible to kind of use computer vision to process this video to actually transfer the motion onto the robot, like this. Yeah. I will show you a little bit more in details how this particular thing works, and especially what I want to show you is one technique used, which is called trajectory optimization, which is a very common technique used in robotics. So, but to sort of give you a bit more detail of this work as an example. So the input is a video together with a simulated environment. Here in the environment you see there is this material, these balls. So really the goal is to transport that, so the reward is to transport that material from this first place to the second place. Okay. But if you want to sort of try to learn how to do it just by, I don't know if people have heard of reinforcement learning, I will not explain it, but there'd be one baseline to do it. It's very difficult because it's a sparse reward. So you have to kind of stumble upon a motion which will transport some material. But instead, what we extract the trajectory and then sort of align it with the environment, and then use it to initialize the motion of the robot. And maybe going a bit more in detail, you've seen we can estimate the trajectory. Then there's a bit of a work that we need to do to align the trajectory with the environment, but we can use the shape of the trajectory to kind of guide the search. But in the end, the real goal is to maximize the amount of transported material from one place to the other. And so the techniques, so once we have the motion of the tool only, we can compute the motion of the robot. And here, this is a technique now, which is called trajectory optimization, a very well established technique in robotics, which is used to compute the motion of the robot in this case, and I will show you what it exactly is done, to explain this equation. but to imitate the trajectory from the video. And to show it a little bit more in detail, so this is also one example. If you haven't seen a robot, this is how, I think it's good to know it because I will touch back up on this. Yeah? So if you have a robot, here is an example of a robot. This is an arm which I think has 6 or 7 degrees of freedom. It has a base which is typically attached to a table. It can be attached to a mobile platform, then it have more degrees of freedom because the robot can move on the floor. So if it moves on the floor, it has an additional 2 degrees of freedom. But here, if it's attached on the table, then each of these joints, it's typically a rotating joint, and it has 1 degree of freedom, and it has limits, which is important. Yeah? You can't sort of go out of the limits with the joint. And of course, the robot has not only what's called this kinematic, but also its dynamics. It has weight of these different elements, and you can model all of that. So here, so typically the node, and I will use that later also, the pose of the robot using this QI, which really, if you have 7 degrees of freedom, it will be 7 parameters, 7 joint angles. So that will be that's the pose of the robot. 7 vector representing the different angles of the robot. So this is the Q. Here is IST at a particular time instance, QT. It's the pose of the robot. Now the robot also has dynamics. So if you want to say pose of the robot at time t, you can compute it from the time t minus 1. If you add a velocity at these different, so each different joint has a velocity, and you can also this is a standard dynamic equation, how you can compute the motion of the robot if you have a control over the velocity. So often what you don't control, you can control position, but also you control the velocity at each joint, or even torque, or the acceleration, if you wish. And then it's sort of governed by this dynamics, and you can use it to control the robot. So here we formulate it more as an optimization problem. And so we optimize over time. So this is the time steps over the, it can be, 10-second motion. So but they are sampled usually much more, maybe, 10, maybe 100 samples per second. And so what you optimize over are, so the V is a vector of velocities. So we have 7 joints, 7 vector of velocities at particular time instance. So here I'm optimizing over the velocities of the robot at all the time instances. And the position of the robot, the base. I also want to place the robot somewhere in the environment. So this is what I optimize over. And the loss. So here, this is the data term. I'm minimizing the distance from the demonstration trajectory, which is the 2 positions. So I have this 2 demonstration extracted from the video. So I want to approximate that with the motion of the robot, respecting the joint limits. And I have some regularization on the speed, and also I have a term which the robot cannot go outside of the limits. And it's subject to constraint, and the constraint is related to the dynamics of the robot. So this is a optimization problem. It is often, I think this case as well, it's depends, I think, what you use in the losses. It often is a non-convex problem. I think in this case, yeah, of course, yeah. So often what you get is local optimization. That's what I want to get to. You don't get often to the global minima, but you get a local optimization. So initialization is important for this. So this is a tool from classical robotics. Robotics people use it all the time. You will see that in the more recent work, when you have vision language models, we don't use a tool like this. We don't use trajectory optimization. Yet, this tool like this can be good for collecting training data. And I will get to this because it's something which you often use in simulation. So you'll see some of the maybe older tools from classical robotics maybe are sort of not used in the latest vision language action models, but they could be used for collecting training data. And so there are also packages which you can use if yes?
May I answer that?
Yes?
So there's the inverse problem, right? You have multiple ways how to get to the target position, but if you optimize this objective, let's say there will be 2 ways, just inspire a object which might not be something that you want, right?
So the question is that there may be multiple different ways how to reach and it's correct there, because you may have the arm like this or arm like that there. So it's so you get one of the solutions. I'm not saying the solutions which I mean you get one of those which respects. So you formulate the problem. You try to usually set up the problem that it satisfies, like you formulate the constraints which are the regularization, so it's the least amount of torque. But of course, there may be a better solution. It's a local optimizer. Yeah. So, but it's a good point. This is a local optimizer, and so sometimes the initialization, of course, matters. Any other question to this? And so there are very good tools to do that. So if you ever end up working on this problem, these are actually developed by our colleagues in France, in Paris, and in Toulouse. And they are actually keep continuing developing them. They are also used for simulation. I will touch upon that later on when I talk about simulation. So trajectory optimization, I will use that in, I think, one or at least one more place in the talk, so I will refer back to this. So some results of the work. So we've developed it. So these are YouTube videos for 3 different tasks, so we see from different people. And we also have like 3 different environments simulated, from which we can transfer from the video to those environments. And I think I don't have so skipping the quantitative results. We did compare with other methods. Of course, it's much better than reinforcement learning with no guidance, because it's a very hard search problem, so you would search forever. But it's similar to, often people in robotics, they would engineer the reward, like so that it's smooth and you can get to it, and you would get similar performance to that, but with video, so no need for engineering the reward. And what's good about this also is that the tool, because it's only based on the motion of the tool, the same algorithm can be applied to robots with different morphologies. So from Panda, which is the one which we had 7 degrees of freedom, UR5 robot, which is 6 degrees of freedom, or even this is the upper body of the Talos humanoid, which is 11 degrees of freedom. The same algorithm, trajectory optimization, can be applied to the robots in this same, because we only use the tool of forget the person, we only use it to regularize, to find the tool of the tool motion from the video. And then we can sort of approximate the tool motion using different robots. So this was an example of extracting motion or learning motion from the video. And I will now, so take this idea, I will try to gradually scale that up to more complicated objects and more data, and you will sort of see where we are at the moment on this, on this task of learning how to do stuff from videos. So one issue which you see now immediately is that this is a stick-like object. So what if I have a bottle, or if I have a cup? How would this apply? And so, and it's right, the current method which you saw does not apply to sort of other non-stick-like objects. But there is a whole another area called object pose estimation, or sometimes 3D, or so 6D object pose estimation. Why 6D? Because, so the goal is, if you have a 3-dimensional object, like a bottle, a phone maybe, or a chair, and you want to estimate the pose of that object with respect to the camera. You're observing that object with the camera. So the camera has a coordinate system, it's a coordinate system, it's a center of projection. I will explain a bit more in detail. And you want to, and it's projected onto an image, and you want to estimate the pose of that object. And often, in this setup, which I will show you in most cases, we know the CAD model of the object. So we know it's the dimensions of this bottle, and we have an image of this bottle, and going to estimate the translation and rotation. Translation is in 3D, 3 parameters, rotation, 3 angles, 3 parameters, 6 parameters of the transformation from the coordinate system of the camera to the coordinate system of the object. So 6D pose, now who has heard of this problem? Quite a few people, maybe half, maybe 40%. So I did include few slides for about this. So maybe I will show this to you briefly again because it is one of these. I think it's one of the oldest problems in computer vision. So for those who haven't really seen it, so this is an image from a paper by David Lowe from 80s. And it's really, I don't have the picture, but it was maybe one of the first computer vision theses by Robert in 60s. And the goal is given an image. This is, it's actually quite complicated image of different razors. At the time they were observing edges and trying to align. They had a CAD model of the razor and they tried to align it based on the edges to the image. So, and it relies, and I will do a little bit of the, again, I'll try to go quickly, but in case you have a question, maybe ask. It seems about half or maybe 60% of people haven't seen it. It really, it relies on the basic pinhole camera model, which is here. So we have a camera center, we have a 3D point which we want to project to the image. This is an image plane at the distance F, focal length from the camera center. This is image point P with coordinates x, y in pixels, which is measured. This is what we measure in the image. And I will go quickly. We can really formulate this. This is a basic from triangle similarity, basic projection. And why am I showing this is because to relate for you or for those who haven't seen it, why it's difficult, the 6D pose estimation. It's difficult because we lose the depth information. We are projecting all the points along this ray going from the camera center to the image plane. All these points along the ray are projected to the single point here. We are losing the information by projection, which is formulated here by dividing by the depth. So this is the y coordinate, and we can write this as the other thing which you will get out is these 6 parameters. So we are the measured image coordinates and pixels are this is up to this up to scalar factor. It's in homogeneous coordinates. It's really showing how you sort of losing this depth information because all these points along the ray are projecting to the same image. You can write this as a matrix form. These are the 3D coordinates of the point in 3D. This is the projection matrix. And these are the focal length parameters. So going quickly, so this would be the internal camera parameters, and this matrix, which is at the moment all one, but this is really it was called extrinsics, and this contains the translation and rotation with respect to the you can think of the object to the camera, and it's written really in this matrix form, like this. So K is intrinsic, this is extrinsic parameters. Rotation is identity, and translation here it's a 0 vector. But these are really the parameters we would like to estimate. I will maybe skip some of the details if you have the calibration. The key important parameter is the focal length. In all the work which I'll show, we assume the camera is calibrated. No, it's on the robot. You can calibrate it beforehand. You know what the focal length is at the moment. But what we really want to estimate is this rotation and translation parameters. Rotation, 3 angles, translation, it's a 3 vector in 3 dimensions from the object to the camera coordinate system. So it's written like this with a calibration matrix, which we assume it's known. So I think it will be in the slides in case, but it seems like half the people know this. I will not go into too much of the detail. Yeah, here's the same thing shown. I sort of like this picture because it really shows how you're measuring things in pixels in the image. Yeah. So you really measure in pixels, but all the points along this array are projecting to this pixel as the information which you lose and which which we can recall because we know the size of this object. We know the CAD model, we know how it's big, so we know based on how big it is in the image where it is. Yes?
Is there any way to solve the problem of if you know the size of an object or whatever, it's like if it's on a flat, you only have a 2-dimensional representation of it. If you just have a a cue to your camera, there's a larger cube, it might like see that as being closer. Is there any way to get around besides knowing depth? Like, can you?
Yeah, so I think this is exactly what we are doing here. So there is the two important distinctions. If you know the camera, intrinsics, the focal length of the camera, then you know the dimensions of the object. So we assume we know the object which is manipulated by the robot. Yeah? So we know how big is it. Actually, you can, from the size of how the object is big is in the image, you actually can recover the exact cost. Exactly what we are doing here. We are kind of using the object, the known object, as a calibration object. Yeah. So because we can sort of recover. So you can do it based on the size. The problem is if you don't know the focal length, then is this what's called the focal. I don't have the slides on this. Have you? But I don't know. Have you heard of the vertigo effect? So you can get the same size of the projected image of the object into camera in two ways. You can put it further, or you can zoom in. Yeah. So you can sort of go closer to the object. You can zoom in, and those it's very hard to distinguish these two effects. And it's possible, but only when you see the perspective distortion. I don't have quite a slide. Maybe if in the Braille do a break, maybe I can show this to you. I don't know if it's interesting for everyone. So it is possible, if you know the size of the object, to recover even the focal length. Because the image of the object, if you are very close to it, there's going to be lots of perspective distortion. If you are far and you zoomed in, it's not going to be lots of perspective distortion. So you can, but it's harder. It's quite difficult. We have a whole paper which sort of is doing that, which is estimating not only the rotation translation, but also the focal length. Yeah. So maybe let's discuss it briefly in the Braille. I don't want to sort of hold everyone in here who knows it, but it's possible to also estimate it. That's an excellent question. Any other questions on pose estimation? Why is it useful? Because I have an image like this with set of objects. I know they're CAD models, so 3D models, I know the dimensions of these objects. And I'm observing it with a camera. I can estimate the relative pose. I can recognize the object, estimate the relative pose. But then, if I have a robot, the robot needs to be calibrated with respect to the environment. So I do need to, if I have a camera observing, I have a robot, I need to know the transformation between the robot and the camera from the base. There are ways to do that. But if you do have it, then you know the position of the object with respect to the robot, and you can just plan a trajectory using, say, trajectory optimization or some planning to grasp the object, like shown here. So this is the very standard, very classical robotics way of doing things. You first look at the image, you look at the scene with a camera or more cameras, you estimate the poses of the object, you know the 3D coordinates where the object is, and then you plan trajectory of the robot, sort of what torques you need to send to the robot joints in order to reach that object, grasp it, and move somewhere else. Classical robotics have been developed. I haven't quite talked about planning, but it's, it is, I think we get away with trajectory optimization only. And you will see at the end of this lecture that now we can do it also a very different way without all of this. And it's quite intriguing. The good thing about doing it this way is that you can have guarantees. You can really, because you have, it's a constraint optimization problem, you can make sure you don't go to the torque limits over the robot, which the motor cannot do, you don't over the joint limits, you do collision avoidance, you have lots of guarantees about the solution. These are the solutions which are used in factories. In fact, if you go to the, I didn't have time to prepare slides for this, I will mention it. Autonomous driving, it's one of the applications combining perception, control, and robotics. There's been a kind of quiet shift, complete shift in the technology. If you go in San Francisco to the Waymo car, who has driven the Waymo in San Francisco? So you can actually go in and have a car without a driver. And it is kind of done at the moment largely based on these principles, that there is multiple sensors mounted on the vehicle, observing the environment, LiDARs, they are reconstructing quite precise all positions of all the cars, objects, pedestrians, bicycles. It's using high-resolution map of San Francisco, which they build, which they update all the time. And it's planning in that environment a trajectory using some sort of trajectory planning, techniques, and then is doing classical control. I'm not talking about control, like basic control, again from robotics, or control to follow the trajectory. That's also what's done in. However, there are sort of new techniques, like a new, I don't know if you heard it was startup Wave from London, who are using more the paradigm of these vision language action models. So it's not doing any of this. There's just a single big transformer which is driving the whole car, but it's training on lots of data. We'll see how, which of these will win eventually. But I think so. There's a happening at the moment a big transition shift in the whole robotics at the moment. Yeah, we don't quite see it. It's coming to both autonomous driving and manipulation. We're talking manipulation here, but it's gradually coming, and we'll see what happens in the next months and years. Yeah. But here, more classical robotics. Any question? Yes.
So in general, are like conventional control systems methods still widely used, maybe in conjunction, or has it largely been replaced by neural nets and reinforcement?
So I would say, I would not say they have been replaced there. I think at the moment, most of the applications you'll see in the real world are using classical techniques, because this is what you have guarantees, it's reliable. I think what we are beginning to see are these sort of new techniques, but the only guarantee you have for the transformer is that, there is no guarantee. So I think I think there's been interesting work into combining the two worlds. Yeah. We are also working on this, but combining more learning-based methods together with having some safety layers, which will and make sure that you don't go out of the limits. You don't. But at the moment, it's you have some training data, which you typically often it's been pre-trained lots of things. You don't know what it is exactly, so you have don't have complete control over this. So it's hard to guarantee it's even in the training distribution. So I think it is. These are the questions that will be sort of addressed by the research community and others. I think the one sort of, I would say, most advanced real application I've seen is the Wave startup who is using these work models for autonomous driving. These are good people. I also know them. I know they do good stuff. But I kind of, how they are. But they are. I think they just rolled out like yesterday. They have a model which they say be driven in 100 cities. The same model. But how reliable it is, I think they are just rolled out like a couple days ago that they are making a deal with Uber. They'll be driving in London, like Waymo is doing in San Francisco. But we'll have to see how this evolves, how it develops. Is it going to be reliable? Probably more stuff will also get published on this in this area. And I think similarly, we see more stuff happening in manipulation. Okay, so any other questions? So I've talked a lot, and I will talk more about simulation. I already will start with one example. This is still in the area of object pose estimation. Yes?
Okay, before you go to the next stage, I wanted to ask if you will talk about how you code or somehow represent the data that you can have from these trajectories or from these pose estimation or object classification. How is, or maybe in the future, how it will be handled to be useful for these models, for these transformers, or whatever it will be. Maybe there will be new maybe second question, maybe not now, but I would be interested. You are talking about a visual language acting model. Do we need this mid-layer like this language?
It's interesting question. So I will try to answer that one already now, whether we need the language. So there is like a philosophical answer, or maybe more like a,
Or maybe a different question. If the language must be our language.
Yeah.
This is then connected with the first question. Like if we cannot somehow find a way how better represent all this information.
Yeah. So the philosophical question is like there is a, and I think I will not take stances. I will just say the different positions. is that one position is that one should be able, especially the acting on the world, one should be able to learn without language. And the real, example are animals. We don't see them speak, yet they are able to navigate around the world and do lots of interesting tasks. Yeah. So they do have certain capabilities which we are able to measure, and we know that they don't use a language, or we are not aware, of like our language. So on the other hand, so I think and there is a part of the community is really there's a lot of work of trying to actually learn representation without language, and it's successful. It works reasonably well. There are also people that to benchmark which one works better, but so that's it. At the same time, we are building, or often Wave and others are building practical systems which are working with humans, for humans. And language, natural language, this is what we use to communicate with each other, and maybe it's also a possibly easy way to communicate with the machines. So that's why it can be useful also to have a layer which will allow us to use that to communicate with the machine. I will show practically how it's used, because there is a lot of actual language data also out there, vision language, and it allows us to somehow map the concepts of the visual world onto the concepts in the natural language, and which may make also the interaction with the human, but also maybe some of the tasks a bit easier. So, but it's and practically just you can tell the robot do this. Yeah, you can tell pick up the yellow object. And if the robot has natural language, it can do that. If it doesn't have the language, you have to point, or you have to have some other way how to communicate to the robot with the object to pick. Yeah. So there is one sort of more philosophical, can I do it without the language? And potentially yes, but it's useful to have the language. Interesting one was, Jamie Shotton, who is one of the co-founders of the Wave startup, where we met at the conference, I was asking him, do you need language, do you use language? And I think at the time he said that, and I don't know about the latest version of the current system, what they've implemented, I don't know. But at the time he said an interesting thing. If the system knows language, it can explain what it's doing. So if there is a problem with the car, if it hits something, you can actually ask the system, can you explain what has happened in natural language? So there is this explainability aspect of it, which may be also useful, is that the system may be able to kind of explain us the problems. Yeah. So he was kind of really pitching as a very good feature that the car can actually explain what's doing. So,
thank you.
Any other questions? So I will. I want to give you a little bit more detail about this. We'll still be talking object pose estimation, but we'll actually do it using learning. There are classical methods which are detecting corners and estimating what's called a PNP problem. I will not talk about those. I will talk about a learning-based method, and it is it's a method which sort of we developed, but it's also it's won some competitions. It's a good method. So if you want to address this problem, it's online, easy to use. We've used it, others have used it. You can try to also use it. And what it's powered. It's a learning-based method, and it's powered by synthetic training data. So what I'm showing here are actually not real images. These are synthetic images generated from, there is about databases of like 50,000 objects, like ShapeNet or Google Scan objects. These are scanned 3D models. One can take a simulator, drop 40 objects into a scene in the simulator, render 50,000 scenes, and render 2 million images of 50,000 scenes. But for each image, we know precisely what object it is and which pose it is, because we've rendered that there. So we have essentially, and we can generate arbitrary number of images like that. What's important in the training is that actually we see, and this is one of the important things, occlusion. Yeah. So this object is occluded by another object which is behind that. But we know everything about this because we've rendered the data. Yes?
The images are generated like in conventional 3D like rendering, not image generation.
No, this is conventional rendering, very good question, but I will talk also about image generation, but this is conventional rendering. It's called Blender Proc. doing ray tracing, different sort of lighting effects, and we can. So it's like physics-based. We know everything about the scenes, occlusions, and everything. We can render millions of images like that. But we know also the ground truth poses for it, so we can use it as training data. And what we can do is train an object pose estimator. How it works, it actually operates in 2 stages, and I think most estimators of this class do that. Is that first, given an input image, it first estimates an approximate pose of the object. And this is done by, somewhat surprisingly, by a classification network. So this is a neural network which is an input an image and outputs a sort of binary score if the pose of the object, has an input an image and a render of that object. You have a cat model of the object, you can render it from different viewpoints. So given an input image and a render, it outputs a score if they are from the same viewpoint. It's a binary, so this is a binary classification network train. It's a very simple setup. Render and image are from the same viewpoint. It's not perfect because you have to, you have to sample the different viewpoints. But if we found and others, it works much better than regression. And why is that? Because the objects have symmetry. So some objects, they look same way from different viewpoints. So if you try to set up as a regression problem from the viewpoint to the, from the image to the viewpoint, it's not very well specified. So usually the regression losses don't work very well. Yes? So the problem is whether this rendered view and input image, which is at the top here, whether they are depicting the same viewpoint.
So how do you represent the space of that? Do you like have?
You have to sample. It's a discretized sample. That's why it's called pose. You roughly get it, sort of.
So is it defined in the continuous space or in the discrete?
In this case, it's in discrete. So I will show. So it's like that's why you discretize the space, and the discretization is important because of the symmetry. So you discretize it, so you don't care if the object looks the same because you get either. So that you get a coarse viewpoint. This is what you see here, and then once you get the coarse viewpoint, there is a refiner, which is an iterative process which takes the input image and a render. This one is not quite, this is quite far from the renders. And then there is what's called a refiner, which this is a neural network, which gives these two an input and produces an update of the transformation. So this is update in 6 parameters, translation and rotation. An update of the parameters to the new, so you can render. So you have the same still input image, but you can now with this update render with a new viewpoint and again run the refiner to update a new set of parameters, and this way in several steps you converge to the correct viewpoint. But it relies on the initialization to be correct. So this is what's called render and compare. So you render and compare and you predict an update. Yes?
And the renderer is trained also, or is it some?
The renderer it's a classical renderer. It's a classical renderer using, you just take the cut model, you render it. So this is the algorithm. Yeah? This is the results. You can see it's sort of relatively stable even to occlusions because we've trained with occlusions. You can see there's still ambiguity if you have rotational symmetric objects. The rotation is so you have some other technique like smoothing that you sort of constrain the motion between the frames. And it's online. If you work on this problem, there's this challenge called BOP, where different people, it's I think around once a year, they compare the results of the different object pose estimation methods. It's done very well, this benchmark and this challenge. This, I think, a couple years back, this method was one of the best ones, and it's open source. Yeah? So you can just download and use it. How would you use it? For example, in robotics, you can estimate, as I saw, pose of the object, and you can plan a trajectory of the robot, grasp the object, and do something. So, and I will show you one more application of object pose estimation. So I've shown at the beginning, you've seen the Atlas robot. So this is the Atlas robot from Boston Dynamics. And I'll show you an example of object pose estimation. So the Atlas robot has a full body motion. So we are not just planning the trajectory of the hand, but it plans the whole trajectory of the robot, grasps an object. You see estimating 6D pose of the object here in the image, planning a motion, grasping the object with two hands and sort of putting it, it's a heavy object, putting it somewhere else. Yeah. So it's one of the most impressive demonstrations I have seen of really like a full body manipulation with an object there. And this is all sort of the classical robotics, maybe with some learnable components. Yeah. So we don't know exactly what they do, of course, but, but building on object pose estimation. The reason I'm showing is also the video because in the, maybe I'll show it again. So they see the object pose estimation. I think what's interesting is not doing object pose only of the object, but also of its hands. Yeah. So I guess so this is, you see this the hands and also the object. We see a little bit outside of the frame and planning the motion. Yeah. Of course, we don't know exactly what they are doing, yeah, for this. The one thing we know is that Luca Manuele, which is one of co-authors of our work, he went to join the Atlas team in Boston Dynamics. But of course, we don't know what they've done in the demo. So, what about YouTube video? So I think this is nice. We have seen we can plan a motion, grasp an object, do a complicated motion with a humanoid robot. But really what we are after, at least in our team, is to try to scale this up to YouTube. Can we really estimate the motion of objects on like a large scale? And I will now show you maybe sort of a couple of results in this direction. So this is a YouTube video, this is the input video, this is the estimated pose of the object. And this is the trajectory of the robot, which is imitating that motion from the YouTube video. Now it's a 6D motion of the object there. It's going again. And you notice that it's really trying to reproduce this kind of a subtle motion of the human, trying to, even the robot is sort of reproducing that, and this would be hard to program. If you want to program this manually, like on the robot, this wouldn't be very easy. Whereas we can really get this sort of somewhat subtle motion of the from the video. And I think, and we still have to show it, that if we manage to scale that up, it will be a way how to kind of get really a large data sets of somewhat subtle motions from video. There is a problem though. I don't know if you sort of realize what the problem is by looking at this. What is the problem?
Overcomplicated, the trajectory that the robot takes. It's just crazily complicated.
You mean with the hands or?
With the artificial hand being above. Like, there are so many useless
motion. Yeah. So at the moment, so this is because we really extract the motion of the object and we just compute the trajectory. It can be done better way. Yeah. But there is one more problem. But it's a good point. One more problem. Yes.
Well, so the can is like radial symmetric?
The can is radial symmetric, it's true, although it has all the writing, so that makes it easier because and I think you're getting at that, we know the writing, but what's the problem? If you want to use this in general in YouTube videos, what is the problem? As I explained before, the algorithm requires us to know the model of the object. Yeah, so in all the work before, even in the Boston Dynamics example, they knew exactly the cat model of the object, so they can estimate its pose precisely. But what are you going to do in YouTube video? So here we are kind of doing a little trick here. Here we're using the trick that, we know it's a Campbell can, and we have actually CAD models of the Campbell can, which is a famous kind of an object. So actually here we know the CAD model of the object, even though it's because it's a famous object. But in general, if you have some arbitrary spoon or a can in the video, you don't know the CAD model of the object. So this is an issue. So we've sort of spent, I'm going to say almost a year trying to, but it is, yes please.
With all these approaches, I have a little bit of a problem because I feel that we get a solution which is optimal for human beings. For certain set of bones and muscles, not for the machine. If we follow this, we will end up with a car which walks or something, because we do, maybe you get to it later, I guess. But with all this copying nature, we have to be very careful. Yeah. Because we get a solution which is optimal for certain, in this case for human being. On the point, a very similar thing. You get a solution which is rather complex, because just taking a can and putting content into the
so
would be probably can be done easier.
Yeah. So here is very good question. I have sort of two answers to this, or like several. One of them is related to Honza's, is that actually what we are working on here, extracting the motion of the object. That's what we are after. Actually, we are not, in this work, we don't care what the human is doing. They may be standing on top of their hand or on one leg. We just care about what's happening with the object. And we found is that this is what we are after, how the objects move, and I will show later also how they transform. Is the bottle going empty or full? So really what we are after here, how the world moves as the outcome of the human action. Yeah. And you may say, well, maybe the robot can achieve some of these things in a simpler way, and it may be possible. And I think okay, so I'll put it in this way, is that we do think that we have a lot of data from the human. So we can at least initialize the robot with what the humans know. And of course, they may be able then to optimize and find better solutions later. But is this initialization what we are sort of thinking about? That's one. And second, this is more like a broader, also related to humanoid robots. Yeah. So is that there is now a fairly big push to build robots which are really looking like humanoids. And you may also wonder why the robot needs to look like humanoids. It maybe doesn't have to have legs, it can just have wheels, and it's going to be simpler. And it's very true. But the argument for that is that if you want to have a robot which operates in the human environment, that is maybe not necessarily in factories, but at homes, assistant robotics, it's useful to have a robot which has similar dimensions, which kind of is looking like a human, because it can operate with us and use the things which we are using. So I think that's the argument for humanoids. It is one application. So we'll probably in future, my estimate is that we'll have humanoids which will work in our environments, help us clean and other things. But in other applications, like in factories, there will be different robots which will look differently because maybe it is not needed for that. But I do think there is a space, and I will just say we have now recently back in Prague, we have this. Also, there's been lots of interesting development in humanoids, so there's some new hardware coming. But we have now beginning a project of humanoids for like a assistive living. And that's been happening for a while, but we think now we can, with the new humanoid hardware, we can also do things like help people to pick up stuff in homes for elderly, for example, or help them. Even I think things like feed people, perhaps. Yes, I think we think we can push this to really like help nurses. Let's put it this way. Okay, so any other questions? Yes.
For this problem, can you you gave the example of the Campbell soup can, and taking advantage of the fact that in most human environments we have lots of mass-produced objects, like your water bottle. They're probably all pretty standard or whatever, in the same size. Can you use those for reference? Like in the image, you see an object that you don't know, but you see an object that you do know. Can you use them to compare and maybe estimate?
So, very good question, very good point. This is the kind of solution which we at the moment came up with. It may not be the final solution, but at the moment, the solution we went with, so we have a YouTube video which was shot by some other people on the other part of the world, and with unknown, actually, even calibration. We don't know what calibration is. It's a hard problem. It's one of the hardest setups you can have on uncontrolled conditions. The solution we went for at the moment is that we take the input. This is a frame from the video. We run some generic object detector. I'm not talking much in detail, but what it can deliver is object boxes, these red things. I will show you a method which can do it better after this. And sort of mask of the objects here. And then we use that to find, we have a large database of CAD models. I would say hundreds of thousands of CAD models. It's, the data set is called Objaverse, which is, depending how you look at it, but it's up to millions of objects. And we come up, we extract a representation of the object, which is, you can think of representing the texture and the shape. It is a learning base, so it's like some kind of a neural network based representation. And we use that to search the large-scale database to not only find a similar object, but also to find its pose, which is roughly similar. Yeah, so we are now not relying on the fact that it's exact, but we are trying to develop a method which will allow a little bit of slack, and if the object is not exact, it will still roughly align it. It's hard. It's a hard problem. So we have I would say, partial solution. And the other thing which you suggested, which is also a good thing, is that now we may know that this bottle, it is hard, because sometimes you have a similar bottle but it's bigger, but for some objects we know roughly their sizes, that laptops are, I don't know, 30 centimeters big, chairs are, certain size. So what we do is, for a given scene, we can also, this is this part, scale estimation. Absolute scale estimation is difficult. In theory, and if you don't know anything about the work, it's impossible because of the depth ambiguity. But because we do know, we can actually ask combination of vision and a language model. We can ask a big language model about approximate dimensions of the objects. And it knows a car is a certain size, and it's not perfect. And because we do it for multiple objects, even if there are some outliers, we can kind of average out the noise, and we can get it somewhat reliably. I would say the error is about 10-15% at the moment, what we measured. It's not, not great, but at least approximately. I'm not giving too much detail. I'll show you some results. Here there are some standard data sets, so it's maybe for more people who work on the question is.
Yeah, I would like to ask some high-level question for that. So I understand that this problem is pretty much very tough compared to what humans have to deal with. Because it is the same, like I want to grab that object, but now I'm going to close my eyes and I'm going to climb the room until I grab the bottle, and I have no sense, I have none. I cannot see the pressure of the object or anything else, and I don't see what I'm doing. Do we have to have very complex stuff like this? Because for humans it's much easier. I just have to move my hands, right? While I have the feedback from my eyes and everything. I don't have to do all this planning.
Yeah. You mean now? You mean the problem in the YouTube, or like?
That kind of have, like, I have to remove the.
So your point is that now I'm on a real robot in a real environment.
You can have the feedback.
And you can have a tactile feedback, like yeah. So.
And you can also see what you are doing.
Yeah.
Maybe you don't have to do it in ideal way, but you somehow see that you're.
Yeah. In the real robot environment, this actually I hope we'll get to it. So at the end, you will see the latest vision language action models. They are doing just that. They are kind of learning a policy which is predicting next steps given my image, and it has a camera on the robot, so it's sort of going to the hand. So it's going to the object and it's seeing it's close, then it's grasping. Yeah. Often it's using depth cameras, which makes it easier. So sometimes I don't think yet quite, but it can have tactile sensors. So I think the vision language action models are kind of doing a little bit like the humans are doing. They are kind of building neural network model which is having the immediate feedback. the issue is at the moment there is no guarantee. If you, in the standard robotics, like the Boston Dynamics solution, it knows, what are the limits of the robot. It knows it won't fail. I mean, modulo it like brakes or something else. So that's the issue at the moment. You have like this whole 50 year of control, planning, and robotics with all the guarantees, which works in the factories, without error for a lot of time. And then you have these. I will show you these. I will get to it. It has an error rate of 60%. Sorry, success rate of 60%. So you complete the task, you reach the bottle 6 out of 10. Yeah. So this is not. You can't put it in the factory. Yeah. So even 95 wouldn't be enough. Yeah. So it's a completely it's a new approach, but it does not have the reliability. We don't have enough data, perhaps. It's like a so. But I think many people have the intuition you have. It should be easier if you have enough data. Okay. I will maybe skip some of the results on the standard data set. One thing I will mention is that the standard data set has a standard set of objects. How you compare results with someone on the other side of the world. Actually, this is a standard set of objects you buy. So you either buy from Walmart directly, or you have it shipped to you, and then everyone, the whole community, can compare how they are doing, because they have also data sets for this. Yeah. But for manipulation of the robot, we can run standard objects. But what's interesting, because we can now do any object, we just retrieve from our database, so there are some objects like the keyboard is not in the standard data set, but our method detected, or there is this chair here is also estimated, because we can now estimate any object which is in our 2 million object database. Again, some more examples. So we can handle multiple objects in the same scene. You see the poses are not perfect, but so approximately they are there. And here are some videos. So this is YouTube videos, completely uncontrolled environment, extracted motions, not perfect. The objects are not, poses are not completely accurate. But at least what we are trying to get is the relative motion, like what the object is doing, and and of course, this is input video, tracked pose. This is the imitated trajectory on the robot. So we compute the joints of the robot to imitate the pose of the object, and we can actually execute it on the real robot also. And so this is kind of running at the moment on tens of videos at the moment there. And we are working on scaling up. And I will show you, I think, basically next is really our vision is, can we scale this up? We have data sets of millions of instructional videos. And the other thing which we observed often is that if the data is not perfect, if it's somewhat noisy, but on a large scale, the noise can kind of average out. So we think even with non-perfect results like this, if it's on a large scale, we'll be able to extract useful information. But it's an open problem, maybe not. Yeah. But in the way of scaling up, and I will now talk. I will try to cover this before making a break in about 10 minutes, but I want to cover one more work. This is very recent, it's still in submission, but I think for this problem, it's one of the best methods there is, based on the comparisons we have on the benchmarks. And it's also an example for those, if you haven't seen it, this is we will build on this for the action as well, so on this material. It's a video language model. So it's a ground. So first, what the problem is, and so how it fits into the flow is that now you see a method which for an instructional video, if you know where the object is roughly, it can estimate its motion. And here we are getting where the object is roughly, but on a large scale. We can run this now on millions of videos. We get localization of objects. And I will show you how we do it. So the problem is, this is an instructional video, someone is showing how to do something, and his input is just the video for the method. The first task which we want to do is output a caption describing what's happening in the video. And I think these videos are relatively short. These are about 10 seconds. So these are kind of single maybe actions, not like a 10-minute task, but small action, 10-second video. We caption it. Man is adding ingredients from a bowl and a cup into a jar to mix them well. So it's a natural language output for the input video. But we want not only that, we also want to identify the objects, the noun phrases, so these are in color, man, bowl, cup, and jar, and we would like to localize them in the video, what's called grounding. It's in the community, it's called grounding, and it's probably, I think in natural language is also called grounding, that you want to not only detect the man in the caption, but also localize the man in the video, ground it. The bowl, which is in blue, it's changing position. The bowl is here, it was here. Cup in green and jar in magenta. So this is, the task is called grounded video caption generation, that you want to generate a caption and ground it in the video. It's hard because also it has to be, you see the boxes have consistent colors in the different frames. So you not only color individual frames, but you also want to actually do the localization in a way that it's temporally consistent in the video. It is a hard problem. And so I will first show you this combination of two things. One of them is a model architecture, which is going to be a giant combination of transformers. But I will try to explain, probably language. I will show you how you can do it for video as well if you haven't seen it. And the second key ingredient, and I think it's almost in any work which I will see, is data. And I want to it's hard to not stress it enough. Often, in fact, the architecture modifications have smaller effect than what the data you have for training. Data is absolutely critical. The more data, the bigger, often not only more, the cleaner, better data often you have, it's important. So in this work, we have two components. One, we propose an architecture. And second, we also have a method and we gather the largest currently data set for this problem. And it's a combination of manual annotation, which we done with an annotation company, with automatic labeling. So it's a method like this. And I will first show you the architecture. So it's not, we are building on previous work, this one on image grounding, but we are extending it to video. It's not this is a fairly, for this problem, it's more like uncommon or like super new or different than anything else. I would say it's a typical architecture used for vision language tasks. It has I will try to explain it a bit in case. I imagine that most people know only language or speech architectures. Have people work like a video language architectures? Some. So I'll try to explain it a bit what's happening. So it has two components. The first component is a captioning component. So it input has a video. It's this. And it's also in video compared to images, it's always memory problems. So you try to, so I think in our case, although we have a 8-second video, we do represent the video using, I think, 8 or 16 frames. So we sample a frame maybe every half a second or something like this, because more fitting in the memory of the GPU is difficult. Or I think you can also do it in chunks. So it's not like you don't think it's every frame 24 seconds. It's sort of on the limit what the current GPUs can do. So it's an input video. You see it's a lower resolution than here, which I'll come back to, and it has time and 336 pixels. Then I guess yesterday you saw Michal was showing you similar architecture. I'll build on what he's shown here. The first this is a video encoder, so it outputs a representation of the video. And the first blocks are often used are what's called a clip. You've seen clip yesterday, yes? A little bit, okay. So it's a representation. You can think of, it's aligned vision and language. It's trained on pairs we've seen yesterday of images and text on a large scale. Works well, successful. So it outputs for takes a video frame, puts it into patches. This standard you've probably seen. Also the spatial embedding, like where the patch of the video is. There is now also a temporal embedding because it's in time. And then each of these patches is put through this sort of clip block, which comes up with a representation, which it's a latent representation of it, but aligned with language. So that's important, is that you can But of course, so here this small box is actually the most of the parameters of the model. It's a language model. It's a llama typically. I don't know which one is it. I think it's llama here. So it's a language model, but you need to map the video into the language space. And how you do that? You do that by using, you have a clip encoder. It's a latent representation of the frames. In this case, it's a sequence of vectors. It's called prompts here, but it's really a latent representation which is coming out of the transformer. A vector, I think in this case, it's for let's put it, it's for each frame. You have a single vector. It's, I think, more a bit more granular for like a subpart of the video. And this is a projection layer, often simple linear projection, which maps it into the input space of this language model. So this one is aligned with language, but in that space, there may be some rotation, some transformation. So you usually need some transformation layer to align this representation with the input to the specific language model which you use. And typically this alignment, you have some paired data of video and language, and you can train this alignment. There is not many parameters to align this video representation, which is already pre-trained to be in language, but you need to align it with the input of this language model. And then the input is, you've done instruction tuning. Who have heard? Many? Not that many. I will not go too much into details, probably you see it later. So you can, instruction tuning, you train the language model to get instruction by the language. So you don't specify the task, object detection you don't train for specific tasks, you train with multiple different tasks, and what the task LLM is doing is specified by natural language. This was called instruction tuning. Here it's specified, can you give a description of this video, a caption, and the video is the set of tokens, the latent vectors, representing the video. It's input here. And the output of that branch is a caption. The caption here is shown in color, but in reality it's a language, it's A, but then there is a noun phrase token which is identifying that specific person, washing a dog, is another noun phrase. So it is a caption with a bit more information identifying the different object. So this is a captioning. So this is a captioning branch, fairly standard sort of parts. These red parts are specific for video. They are trained, so fine-tuned because it's pre-trained on still images and also data to work with video. So this is captioning, and now the second part, but I think I will do it still in the last few minutes. There is the grounding module. This is the second part, which is actually predicting the bounding boxes, localizing. So this is done, so you see there's also video, but it's on a higher resolution. And again, it's a little bit kind of, ideally you would do everything on higher resolution, that is not enough memory. So you kind of, I think these architectures eventually will maybe go away or will be replaced, something more compact. But at the moment, we are operating on the memory limits of the GPU, so we try different ways, and others try different ways to kind of fit our problems into the current GPUs. There is another latent representation, which is specific now more, so it's really representing the individual, it's bigger, it's representing the individual patches, it's done for localization. And these VITs, this is vision transformer, you've seen yesterday vision transformer, yeah, so you know vision transformer. So these vision transformers, they are not necessarily aligned with language, it depends how you train, but often they are pre-trained on some kind of masked task or like a next token prediction. But they are, more fine-grained. They represent more localization information. They are individual patches, and so this encoding of the video, which is more specific for localization, is coming into this bounding box decoder, which is a language model, but this is trained specifically for predicting boxes. So it's predicting. So this is T is number of frames, N here is the number of objects. And 4 here is the coordinates of the bounding boxes. Yeah, so we have a sort of 2 points that specify the bounding box. So it's really represented by language. It's outputting the bounding boxes as coordinates in the image. I think it's a normalized image plane language, it's another transformer which brings it, but the transformer takes input the video tokens from the left in high resolution, foreground and for localization, and together with the caption representation, but it's really from this LLM, these are the for the individual objects, but they also contain the not only the language token, but also the latent kind of contextualized representation of from the last layer of the transformer for that specific token, and it's coming here for the object tokens for this one and this one, so it's 2. So here n is 2. You have a dog and a person. And for these two objects, you get a bounding box and some confidence score, how likely the object is in the video frame. Sometimes you have occlusion. I'm occluding, this bottle here, so some frames you won't see it. So we're also predicting that. So you can see it's kind of a combination of different transformers, which are pre-trained on different data, but trained together on this task for grounded video caption generation. Yes.
So just for clarification, the two videos are the same, just the resolution
is the same, yeah, just the resolution. I think this will go away eventually.
Okay, because it's fine. That's some engineering tricks, but
I think this is often people do it this way because you need higher resolution here, and it's sort of hard to fit in everything into memory. Any other questions? So I think it's kind of speech language, we are all converging into the transformer. So I think you can understand a fairly complicated vision model because it's a combination of transformers and language models. But as I said, the key issue is the training data. And so these are some of the existing data sets for this and related tasks. There are the number of videos and number of annotated bounding box instances. So we have iGround is manual annotated with work with a company which we sort of produced about 2,000 videos which are annotated with these boxes. But we also, and I will show, I'll go quickly, but we basically have a semi-automatic method where we can scale this annotation to our scale. So we in the end have a data set of 1 million videos with 80 million bounding boxes which are sort of annotated for this task. And it's the largest data set for this problem at the moment. I will show briefly how we do the automatic annotation. So we can apply a still image version of this algorithm on individual images, frames of the video. We get sentences, but they are inconsistent between different frames. You have one sentence for one frame, another sentence related but different for another frame. The boxes are, in this case, are the kind of same, but they don't have to be also. They can be different colors. You don't know the temporal continuity. But we can use a language model to sort of combine the sentences, aggregate them into a single video consistent representation. And also to then label the boxes in a way that's consistent over the video. So this way we get imperfect but sort of large scale annotation, kind of improve. And that's I think one of the also recent trends that people are taking existing incomplete data sets and extending them using often processing by language models and other techniques to incomplete, somehow improve, denoise the annotation. So this is an example of this, and it does really help. So this is pre-training data size. So how much of this data which we sort of annotated in this manual manner. We also combine it with the manual data which is clean, and so more pre-training. And here is two different problems, captioning and this object localization. Higher the better. This is a CIDR, one of the standard, not perfect, but standard captioning metrics. AP50 is a localization metrics, how well we predict the bounding boxes for the objects. You can see that, and this model, the green one is zero shot, before we apply our manual training data, and the red one is after the fine-tuning using our manual, careful, precious thousands of annotations collected in collaboration with the company, done by humans. So of course you see by humans, it's a big improvement by the clean data, but we do see an improvement, especially in grounding, by the manual, by the sort of automatic large-scale data. And it's non-trivial improvement going from say 30% to 43. It's a fairly significant improvement by this automatic annotation process on a large scale. And it also has currently the best results on the existing data sets. And I think more importantly, we were quite surprised by the results. So these are examples. I think actually it's random. We sort of looked at the results. It's not super picked. And this is always the caption with the color-coded noun phrases and the localization of the objects for different sort of YouTube. These are YouTube videos, so it's very wild, in the wild data, not curated. One of the hardest, I think, data we have for this one. Yes?
I always have problem with these data sets and such, because most of it is understandable from images. For most of the descriptions, you don't need the text. So, how much actually is the video important?
So it's an interesting question. We do have in the work, we do have comparison with the still image. If you just apply it on center frames, we do have some improvement. But the second, I think our main motivation for doing all of this is actually to extract the motion of the object. So I think we kind of, so why I'm excited about this is that I'm hoping that we will feed the output of this method to the previous method, and on a large scale we'll be able to estimate the motion of the bottles for like thousands of different bottles in the video. Yes, I think, or the spoons. Yes, like on this. So what's important for us is not only the language description, which you may get kind of from the single image, but actually the tracking of the different objects in the video, their motion, the localization of the object, basically.
My point sort of is, like, it's memory intensive and so on, mostly because it's working with video. So what if I just train everything larger on images and then apply it to video? In my experience, like, the image things work at the end better.
So we do have comparison with image methods. Of course we haven't done we didn't scale up existing image methods yet. But we have comparison with image methods. But I think we did try also some. You can also say, well, I just get it from a single image and then I do tracking. But we found actually tracking doesn't quite work because often actually these videos you change viewpoint to some extent. So tracking completely fails. So here it's kind of doing a bit more than tracking, because I mean maybe we'll see a video where you see kind of flipping viewpoints and associating. Maybe this one I think has it. Yeah. You see it's kind of, and it's still all correct with like a changing. So tracking will not work in this case. Yeah. So it's and we do have reviewers also pointed it out. So we run these comparison tracking methods, and it's better. So yeah. So here we go, and I think that we are now really first creating a demo. You can search. We want to scale it up with 1 million videos. We want to scale it to multiple millions, and then start really feed this data to our robots somehow. And we will be very different ways. So there was a question here earlier how to best feed it. I think we can discuss it once I show the vision language action models. There are different ways. You can try just boxes, just language, also the 6D poses of the objects. We'll try everything probably, but it's. I think kind of my at least motivation doing all of this is actually to feed it to the robots. So let's do a break for 10 minutes. Yes.
For these videos, then it was manually annotated for training the counting boxes, or it was somehow automatically.
So we have 1,000 videos which are manually annotated with boxes and captions. And the rest 8 million videos which are done automatically. Before we continue, we have to kind of cut at the end. Any questions to the previous?
I don't know. Actually, somewhere on slide 20 or whatever you were showing the situation for planning the trajectory. Mm-hmm. And of course, there were like one cost or one was there for following the trajectory. The second one was there for, I think, like this one. So I wonder about the third one, respect joint limits, because usually in like the speech or language, now we know that things sometimes break. You get wrong answer, like the word is not correctly recognized. We live with it. We have vertical rate or blur score or whatever, but if something happens to you, you will break your robot. So is there any way to impose some kind of like hard constraints, like this term in the minimization simply cannot be ignored?
Yeah, no, I think it's usually there is like always between a constraint and an objective. You can kind of formulate in both ways. Actually, I don't recall now exactly what the details. We could look it up after how it's done. But I imagine this would be some kind of because this is a really hard limit. You can't go over it. So I imagine it's going to be some barrier function which you can't really do it. So it's a. And I mean, this could have been also, this one could be also here in the constraints. Yeah. So you're completely correct. These are hard constraints. Yeah. This one, it is here, but this one is more the regularization. But this one is a hard constraint which you want to. Yeah. Very good point. Any other questions? Okay, so let's move to simulation. So one would think, and that's what I thought also, that simulation, oh, this is gonna save us, we're gonna simulate, it's gonna be fast, and you know, it's gonna be the solution for robotics. And for me, it was somewhat sort of surprise, this somewhat cold shower, is that simulating the real world is just difficult. It's not easy. And there are different aspects which I will touch upon. But one of them is the complexity and the variety is just huge. Yeah? So this is an example image from Prague, and you see the variety of the different people and the clothing and the complexity. They are all kind of layered here, although the perspective you could probably do. But so there's a huge variety of objects. That's one. But also simulating the relations and the physics accurately also turns out to be difficult. Yeah? So doing accurate and physically consistent sort of simulation, even like simulating, our fingers are somewhat soft. So for me, it was surprising that even simulating the interaction with like objects, which seemed this was also a little bit soft. So like simulating it realistically, the world, even the physics, is just not easy. It's not a soft problem. So so it's hard, but there are successes. So I will show you some of those. This is not work by us, this is work by others. It's very nice work by the team of Deepak Pathak at CMU. It's called Extreme Parkour with Lect Robots. So they have a quadruped here. I think it's one of those Unitary, so it's about $10,000 or this. It's not that expensive. Yeah. So really quadrupeds and even humanoids have come a long way in few last years. Even the hardware is gotten cheaper and better. It's equipped with a forward-looking camera. So it's a camera, it's actually depth sensor, which is sort of measuring, I don't know, frequency, maybe 30 hertz, what's in front of the robot. And the robot is fairly lightweight, as you will see, but it's, it is a robot which is walking. And they've taught the robot to do this. So this is a sort of parkour course. And so there is a controller on the robot. It's entirely trained from simulation. I will show you a little bit how. But the robot is trained, and I think it's not just for this, like for the specific, you can actually move the obstacles to some extent. How much? I don't know. But it's not like some of the Atlas demos that are kind of very carefully curated for the specific scene if you move it by a little bit. This is really a trained controller in simulation for the robot to walk around and do this. But what's surprising, what's impressive is that it actually can do fairly extreme motions. It learns to do fairly extreme motions, so it's jumping twice the height of the robot. Here, yeah. And on this other video, it's jumping across a gap which is twice the length of the robot. Yeah, so it has really learned these motions, which are fairly extreme, fairly difficult. Yeah. And I'll show you a little bit more what it has learned. It has learned to do a handstand, which is also it's sort of walking on the front legs. And by the way, this is all a train. So it's really input is an image, and output is a motion of the. It's like a voltage on the engines of the legs of the robot. I think I don't know if you count, we have actuators, so there are one actuator here, one here on each of the legs. So it seems it has maybe, what, 8 degrees of freedom, maybe a little bit more if there is moving parts. So. And I don't have too much detail of this, but I want to kind of show you how, on a roughly, you get an idea how it's done. So these, and I will stop it, I think, for the moment. More details are in the paper. So what's interesting, it's trained in 2 stages. So it's really trained in a simulated environment. And so let's first forget about the bottom, let's just look at the top. So it starts with an environment where the robot knows, I mean, what it's called, it's not the state of the environment and itself. Yeah. So there is so what's called proprioception are the angles of the robot. So this is the measurement you can take, the robot can sense, of course, what are the angles of its legs. So it's really the pose of the robot, that's called proprioception. And in this simulation, this is what, it's only learn, no images, no input from the camera. First, it just learns to do the motion as if it sort of knows only the environment. The environment is senses these scan dots. This is how it senses the environment. It knows the environment, and also it knows what's called the oracle heading, like where it should be going. Yeah. So it's sometimes it's called curriculum learning. It's trained to do a simple task, simple problem where it knows more information which will not be available in the real world. But it's trained on this simple problem first. And it's really trained to sort of position, move the leg in order to move across the course, and there is a certain level of randomization. The simulating environment can have different obstacles, it can have different heights, you can add noise to the environment, and you can train the robot. And the controller is quite simple. In this case, it's a MLP, it's just to be fast, so it's a multi-layer perceptron, which takes as input the state of the environment, which is the scan dots around the robot, the heading, the state of the robot, the proprioception, and it's producing the next action of the robot. So that's in the phase 1. So you train the robot for a while on this, yes?
The proprioception, is it just the kinematics of its limbs or also the dynamics? Does
Yes.
it also the pressures?
The truth is, I don't know how to reread the paper, what exactly they use, but you could imagine in this you have access to both. Because it's in simulator, you know everything about the robot, and you know everything about the environment, so you can use as much as information you can.
There might be strain gauges.
And how exactly what they do, if they use just the position or the also dynamics, I don't know, we can check it there. But the important, at the moment they kind of use more information, and only when they train the robot to perform well, if it knows everything, the latent kind of state, only in the second stage they introduce the camera. The good thing about, or the simplification, is that simulating real world pixels, like including color, reflection of the objects, color of the clothes, is hard. Depth sensors, in especially these simpler environments, are easier to simulate because they are just less complexity. So they rely on the fact that they have a reliable simulator of the depth images received in the sensor in their simplified box world of the boxes in the room. It goes on the grass, so they can do a bit of an outside. So they can actually reliably generate observation of what the robot would see in the camera. So so they copy some of the controllers which they train in the simplified setup, and then they start simulating the camera. Here, this is GRU. It's a gated recurrent unit. It's like LSTM, so it has a little bit of a, you probably know this also from the language, it's a recurrent network. So they use that to represent sort of a little bit of the I think also the history of the observations. They use that to predict the heading, which direction they have it observed here. They use it to predict the heading, which direction it should go. They have proprioception from the real robot, which they can measure. And then they use that to produce the action, which is the voltages on the motors on the real robot. So they have this curriculum learning from first in simulation with the known state, and then in simulation also, but they also simulate the observation of the sensors of the camera, what they will see in the... So I kind of stress it because this, being able to do that is not often the case. So this is special in this somewhat simplified setup, so you can simulate fairly well what the real observation will be. Yes?
So in the first phase, the movement was based on some physical, let's say, optimal movement, or how did they actually generate it?
I think first of all, these courses are relatively simple, but I think they use, the truth is I don't know exactly in detail if they use some sort of trajectory, so if they sort of, given the state of the robot, they can actually compute that, but I imagine either of the two, and they can do it on a large scale, so I imagine they can really sort of compute, and there are actually these kind of trajectory planning models which can do that. Yeah. The other option would be to use somewhat a bit of reinforcement learning, so of letting the robot also discover, and maybe they use a combination of both. That's a good question. So I'll now play the video so you can see it, and so just from these observations, and it's kind of learning because it's in front of it there. So it's sort of learning what will be below the legs of the robot in a little bit, so that it can position the legs. I think it's quite impressive. It will be very hard to model. Okay, it's possible. Boston Dynamics have done it. They kind of have observations. They can do planning. You have to really plan your footsteps carefully. That's how it works. It's like a hierarchical planning problem. Yeah? Then you have a controller which executes the planned motion. But here, the robot kind of, just from these observations, it kind of learns the relationship of what the terrain will look like in a little bit when I step there in whatever, a second. So I find it as a fairly, yes?
So how can you control it once you train? For example, how can you force it to work on the front?
Yeah, so I think so here it sort of predicts the heading. I think you can also potentially sort of, I don't know if they do it here. Yeah? So I think in the paper, if I'm so recalling, they set up a goal. Yeah? So kind of they set up a goal where the robot, which direction it should go overall. But I think you need to have some mechanism where you specify the overall direction. Yeah? But I think this is more about the local control, like you can actually do the walking, few steps, do these jumps and things like this, about the overall planning of the path. Yeah, so I think when I came out, I thought, oh, this is quite impressive. But it is kind of, it's an example of a simplified setup in a simplified world of the boxes. And it's not quite sure, we don't know when it's going to fail, if it's going to work, if it comes here, we don't know. Maybe it will, maybe it won't, because it sort of depends how similar it is to the training simulation distribution, and is it going to walk on the stairs here? Having said that, similar techniques have been also done in different places, like Jitendra Malik had a paper on where they also had the robot walking around. I think ETH, they also had the robot like walking in the mountains even. Yeah. So I think this kind of technique, first of all, quadrupeds as robots are getting mature, the technology, the hardware, and I think on this walking locomotion for quadrupeds, it's getting fairly reliable. Yes?
I'm wondering how they handle some generalizations, something like it. Is it fine-tuned in the real world?
I don't think so. I think it's, and I asked Jitendra Malik has a similar work, slightly different, and I also asked them, and I think the key idea here is called domain randomization. Is that in the simulation, you randomize the simulator. You pay, here you see the environment is not completely flat. Yeah, it's not a flat plane. It's sort of random. It sort of mimics the unevenness of the environment. And I think you can actually add increasing amount of noise. I think Jitendra did some of these experiments. So you can increase the amount of noise, how bumpy it is. And so I think, so this is one intuition which I thought, for me, when I sort of realized that it was, I think it's an important one. So in this domain randomization, yeah, so for a while I thought for something like this to work, you have to have like a photorealistic, real-world realistic simulation for training. Yeah. I thought for a while. But then I think the idea of domain randomization, so you can imagine that there is like a, some space of like really photorealistic images and scans and environments. The idea of the domain randomization is that you don't need to have that. That all you need to do, so if you randomize kind of, say, the height of the floor in certain way, or even they may be adding certain level of noise to these images. If you randomize them, all you need to do, and you train on all of this data a lot, you train with randomized data. So all you need to do, you sort of require is that the true manifold lies within the randomized one. And I think that's a very kind of interesting idea. Is that, and people also do that, and we also did it. So in vision, a good idea, a good example is that, when you have a background, you don't need to have photorealistic background. You can do lots of different backgrounds. Like they can be sort of random textures, and it actually the neural network learns to ignore the background and more focus on the shape of the object. Yes.
Do I understand that in this case there are no pixels, and if you have that, then it might generalize much better than if you would have real world?
Yeah, I think so. Yeah. Also, the depth first is a real measurement metric. Like it knows when it sees here that it's 50 centimeters, and it kind of can measure it can learn the relationship. If you walk this fast, this will be when I get there. That's why I have to put So I think it's important. And second, it's less complex to simulate. You don't have to model reflections, colors. So it's
Exactly, because I don't know if whatever you said with the manifold would hold if you would have images like pixels instead of the depth.
So in people also do this idea of domain randomization in pixels. And in this case, it's more that you kind of randomize. It's not, of course, it's not like a random noise like Gaussian, but what you do, you randomize the textures of objects. And this has worked surprisingly well, although it's true that what I've shown, like with the object pose, in the end, if you have a good simulator, it works better. Only you need less data. So I guess maybe intuition, if you do have that, you should use that. But if you don't, or it's hard, you may need more data, but I think this kind of goes over the problem. And they also do it, by the way, this holds for other parameters of if you don't know, for example, we used it in other domains, if you don't know the weight of the object, for example, you just do lots of simulation with different weights, and the controller learns to kind of, work with different weights of the objects, even that, your specific one doesn't work. So domain randomization is quite powerful concept.
Do you know if there are some other sensors, like some?
I think the robot. This robot has the camera and then the proprioception. I think the proprioception, it is kind of acting a little bit like a sensor, because if you look at this, so it measures all the time the position of the legs. And here it's sort of, so it's realizing it's slipping. So I think it can learn the control when it sees it sees it slipping, it sort of learns to do something else. So I think that the legs are acting kind of as a sensor, because you observe their motion, you observe their slipping and things like this.
So do you understand that this behavior was still learned in the first place, that there would be some kind of slipping, so it would be aware of it, or it automatically discovered it?
Yeah, so first of all, I don't think they specifically, I think all of it is discovered. So I don't think they specifically, basically they don't train specifically to do this. It discovers this motion to overcome these obstacles. Okay, so very nice work. Another example, this is from the Jitendra Malik's lab on in-hand manipulation. It's not an easy task. It's a fine sort of grain manipulation. These hands is an Allegro hand. It's not super expensive. I think this one is about $10,000 or $15,000. Some of them are $100,000. And also it's sort of relatively big, so they also have to do it with bigger objects. And it's also learned in simulation. I think here you see the idea of domain randomization. They kind of do the simulation with different objects and different weights, and then the controller kind of learns to do it. There is no vision here. It's also just based on the proprioception of the fingers. And they can, these are real videos of real objects being sort of rotated. It's very impressive. I like this work a lot. That's why I show it. At the same time, I was later at a demo at DLR, which is a German space center, but one of the most advanced robotics labs in Europe. And they say this is the easier problem. The hard problem is do it this way. Because in this way, you really have to, it's not, here you only have to compensate for the gravity, and you can kind of, here you have to do the forces. Yeah. And so they had a demo doing it this way, but even this is impressive, I think. But one can go further, yeah, this is not the end. Doing it this way is hard. Okay, moving forward, this is another example. This is actually work from Karel Zimmermann at ČVUT in Prague. This is kind of, I show it more as an example. They have this robot with these articulated tracks, yeah? And it's meant to go over complicated terrain. The robot has been part of multiple different European projects, which they also did with safety missions with like fire department. And it actually has been really deployed. There was an earthquake in Italy, and sort of a church went down, and I think they deployed the robot at the time that it was kind of not secure to go inside, so the drone went in and the robot went in to kind of see the environment, to map it, after the earthquake. So, and this is an example of a work where they, here at the top you see they have some estimate of the current environment. They are planning the trajectory of the robot, but here it's not just moving, you also control the flaps. So you have to not only say what torque you put on the track, but also how you're gonna do the flaps in a way that you move across difficult terrain. And I'm sort of not giving all the details of the work, but they also have a method. First estimate the terrain, you can go down the stairs also, and they have like essentially a simulated environment where they can simulate what would happen, and then they can sort of train the robot to do these different tasks in this simulation so that they can deploy it in these environments. And I want to more show it because it's been also deployed in the DARPA is organizing different challenges, I'm sure also some in language and in speech in your area. This was a DARPA challenge called Subterranean Challenge, which was about exploration of kind of underground environments. It had different parts. You can see, this is an example. Some of it was like a underground concrete built environments, but some of it was like really tunnels, like caves. Yeah. And the goal was for the robots to go inside and explore the environment and find objects, like find a person lying on the ground, find a bottle or things like this. Yeah. So that was the task, and it had to do, it was not auto, like was teleoperated, it could be. So there was constraints, you can have like 2 people on the team, you can have multiple different robots. And of course, the more autonomous, the better, because the people could not teleoperate everything with the limited budget, but usually the winning solutions were combination of some autonomy of the robot, but combined with sort of a human guidance. And so these robots also went in, was going for multiple different years. Here's an example of the robot kind of mapping the environment, creating a local map and doing some kind of a planning. You can also think of it, the planning in the environment as kind of simulation, because you're simulating different paths you can take, you try to find the optimal path through the environment. So I want to show it as an example of the application. I also want to, these are not my results, but I still find it impressive. So in the first year it was run, they were the best. So some of the funding, some of the teams got funding from DARPA on this challenge. And so the ČVUT team, the students, they were the best non-funded team, so they were 3rd overall. And they were the best non-funded team. And apparently what I've heard, during the competition, it was really sort of some of the teams like MIT or Stanford, so they really did well among like, some of the best robotics teams in the world. I can, so I think it's a very sort of nice example of work. I think they were sort of coming, they did the competition also evolved, some of it was in simulation, it was more open, but I think it was a nice success. And so before I move on, I want to also mention this really simulation is really becoming one of the major sources of data now for the robots. The simulation environments are getting better and better. There is just listing some. I asked my students to also list like one of the most common ones at the moment. I think NVIDIA is pushing this a lot. Yeah, so they are putting a lot of resources to develop this environment so that other people can use it to run on NVIDIA GPUs very quickly. But there are sort of different ones, they have different properties, and there is a lot of progress to make it more photorealistic, to make the physics better. But, and we also use them. But I do want to mention it's not a solved problem. So Justin Carpentier, our colleague from Paris, he's working on building simulator, making the physics more accurate. This is a paper comparing different contact models for robotics. So the point he often makes is interesting, is that, of course, simulation has been around for a while. A lot of it was in computer games, and it got like very nice. But especially the physics in computer games doesn't have to be physics accurate. Like, you know, it has to look good, but it, you know, it doesn't matter if you generate torques which are impossible, or if you don't respect the joint limits, because no one will notice unless it's visually kind of difficult. But for robots which are really deployed in the real world, it's important that it's accurate and it respects the physics well. And he spends a lot of time on designing and comparing different simulated models.
What do you mean it doesn't generate torques?
Doesn't
generate torques.
Okay, so I meant. So imagine, usually how it works, even what I was showing, yeah. So in the trajectory optimization problem, which I was showing at the beginning, well, maybe I will not show the slide, but the outcome of the optimization is actually velocity or even torque of the different motors on the robot throughout the time. Yeah. And you optimize the problem and you find a solution. And we even found in some of the earlier work that the solution which we were generating was a torque which was impossible to do by the robot. The robot just cannot physically, by the motor, cannot like create or generate such a torque. So our model was suggesting the robot should do a motion. You can imagine, like, you know, it would be for a human, we would say, lift this 200 kilo thing, yeah, so the human cannot do it. So the solution may come from your trajectory optimization may not be feasible for the robot. So you have to come up with a solution which is feasible. And different robots have different constraints. Some can lift more, some can lift less. So I think that's what I mean, that you have to sort of respect your constraints. Does it answer your question? Yes.
So, what are your favorite, or what do you think are good simulation environments these days for robots? And what do you think about the simulators which are developed by NVIDIA, for example?
So I kind of, yeah, maybe this is for like a longer discussion. We are building at the moment, like the work which, and I will come back to it later. At the moment, one of the issues in robotics is hard to compare different solutions, different teams. So we are building a simulator, like a not simulator, a benchmarking environment where people could compare, especially focusing on generalization. And I think we are actually also comparing. I don't think I have a concrete answer. I know we are using many scale. And I think all these ones which at the moment we are at least considering at the moment, yeah. So, and even the benchmark may be using two different simulators just to be sure that, you know, there is some variability. Yeah. So I don't have like a concrete answer, you should use this at the moment. I do want to mention one thing. So Justin Carpentier, who is on this slide, when you talk with him, he says, all the current simulators are wrong, the physics is wrong, you have to do it properly. So he's really developing like a new models which are modeling the contacts, both like rigid but also the soft ones in what he thinks is better. It will have to be still shown. I think some of it he's already demonstrated. They are better. His simulators are good. So even famous places which I will not be naming are interested in the work which he's doing. But I think it's still out. It's ongoing work. So it's still an open problem. I think that's kind of my answer is I don't think it's a solved problem. So you may have a preference. I would say, don't commit to single simulator at the moment. Try different things. I know this is an engineering effort, but and better ones may come.
Ask differently. So, for example, if we had students who want to do some reinforcement learning or something like that on reasonably well simulated robots, what would you suggest?
And I think what's interesting is also, as I asked, so Martin Sedláček, who prepared this slide for me, they have different, like if you want speed and scale, you go for Meniscale. If you want visual quality diversity, you go for Genesis. If you want precise physics. So I think at the moment they're that's why I'm saying there's no single silver bullet. I think at the moment they have like a different advantages, and it's not and Justin thinks the physics is wrong in all of them. So he's developing a new one. So I think it's still, and it's not that's why I'm saying simulation is hard. It's not a solved problem. So, but we can discuss, let's discuss later. I can maybe even connect it with, my students, and they can tell you what is changing. Right? We started with Meniscale, now we use a different one. So we can tell you what are our latest things, latest thoughts on this. Okay, and one more thing I want to mention: simulation is at the moment is also hard to get it physics accurate. And even if you get it, there are two things. One of them, simulation, and second, even the hardware which we have is, kind of compared to human hand is amazing. Yeah. So even the kind of actuators which we have are somewhat limited. And even the way we simulate the physics, so kind of making two somewhat convoluted points. Both the physics is hard, but even the hardware is not great. But the reason I'm making these points about the simulation is that maybe there is a different way how we can simulate. Maybe we don't have to kind of simulate the physics and everything sort of based on the physics principles. Maybe we can learn it. Yeah. And I think this especially becomes important in areas where the physics is becoming very complicated. Like, this thing, well, maybe you can still model it in a good way. But what about a pineapple? Yeah. So imagine you have to model physics, like a proper physics of peeling and a pineapple. So, or more like cooking food. These are squashy objects. You cut apples. Like modeling the physics of it may not be easy. Or if you want to, even like a simple meal. Yeah, if you want to make an omelette. Yeah. So do you need to really model the physics of all the cooking and the transformation of the food and the temperatures there. So there is a whole, another sort of branch of what's sometimes called like world simulators, which are just learned there. And they are sort of, maybe you don't have to sort of generate, maybe they'll eventually be all 3D, but they're generating observations. I will show you examples of our work, which is kind of getting, and also then later on, these world simulators. It's really a thing which is now happening, and it's even for self-driving, even for robotics. The example, I will start simple. I will not do like a whole simulator. I will just want to change one image. I want to change one image. I want to say I have an input image like this, and I want to, with the language, I want to peel it on a chopping board. But not like, I don't want to do the stuff, it's too complicated. I want to just imagine how would it look if I peel it on the chopping board. And or if I then put it in a blender, and if I make a smoothie. Yeah, so I'm kind of, rather than doing the physics simulation, I'm imagining how the object is going to look like after the transformation. But the specific one, we call it transformation of object states. How the states of the world or the object are changing if you do human actions on them. The work is called Gen How To, and it shows, this is the peeler, this is in the blender, and this is after you blend it there. So, I mean, one could simulate the physics going from this to this, but it may not be that easy. Yeah? So, but here, we are just going to train a generative model, which is going to, based on training it, so this is how it should look blended there. You can, of course, and we can do it for a different object. We can do it for an avocado as well. And you can say, well, we have generative models like Midjourney. I'm just gonna do it. The problem is that what we want to do, we want to change the object, but we also want to keep the scene. We want to keep the same object there. So your input, which is the object here, this is our method, the Gen How To. And these are some of the sort of best sort of instruction guided generation methods. So you can see that for them what's hard is to keep the scene consistent, keep the same cake. Here is, you want to frost it with strawberries. Yeah. Here this method is changing also the cake. So, and I have some sort of more examples here. Is the scene consistency, which is hard. So what we are going to do here, we are going to take a generative model and fine-tune it on videos of the instructional videos from YouTube, where we see the same object undergoing different changes, and we're going to train the model to generate these changes of the object for the specific input scene. So we kind of training you can think of it as a video generation model, but the video generation model is not doing whole video, but only like a kind of keyframes or like these changes of object states. And I think I will speed up a bit because so that we are not. I want to get to the vision and language action models. So I will maybe go a bit faster if I manage to. Oh, here we go. So there are kind of, I will try to go quickly, skip some of this thing. The first thing is how to get the training data. So we will spend, again, a lot of time to gathering appropriate training data. And of course, the second is how to, I'll skip some of these details. Gathering training data for this problem is not easy. I will skip some of the details, and but I will talk a bit about the model architecture. Who has, and I think this, I will try to go quickly, but still I think it's an important, kind of a area. Who has heard of image diffusion or diffusion models? Oh, many. Okay, so I don't really have to explain it. And latent diffusion. A bit less, but still many people. And who has heard of control net? 2 or 3. Okay. So I will maybe go somewhat quickly. So image diffusion. Image generation for a long time, when I was doing my PhD and after, was thought to be one of the hardest problems, to just capture the variety and compositionality of the world. But of course then, and there were different sort of, a lot of progress using GANs, for example, but really the results of the image diffusion were sort of, becoming like very good, basically. So we're really kind of nailing the problem. I don't think it's completely understood why it works so well. So I think we know that it works, but like what exactly is the necessary why it works. But so I'll give you a little bit. So this is the architecture which we do for the single frame change. So here it's a slightly different problem. We don't want to generate any image, but we want to do the specific thing of changing one image of the same object, changing the state of the object based on, we want to keep the consistency. And describing by language, we want to see how the object will change on this when you want to say avocado halves on chopping board. So we are kind of conditioned, you can think of it in terms of if you know image diffusion, you want to condition not only on the description by the language, but also on the input image. Yeah, so you want to be consistent with the input image. And I will show you in a bit that we can do it for like a sequence of images. The other important components, there is a noise component, and so the method we build on is called control net, which allows you this conditioning on an image. So you probably know that an image diffusion can condition on the text. There is the latent diffusion component, which is you have an encoder where you encode both the input image and the noise. There's this, so here is the decoder, which then decodes to the image space. You operate, diffusion operates in the latent space. That's why, it's efficient. Latent diffusion was a very important, very nice innovation. But there's this condition on the image, which we put through the same encoder. So we put it in the same image space. And then there's the part on the control net, which I will maybe show, which allows you this fairly, I did have one slide on diffusion, but it seems everyone knows it, so I will not talk about it. The latent component, latent diffusion, you don't do it in pixel space, but you do encoder, pre-trained encoder, decoder, you do it in the latent space. Yeah. So this, I think, it seems everyone also know it. Often, we use these UNet-like architectures as for image generations are very good. And this control net component is an interesting one. It allows you to condition on an image, basically, or on some image level like information. The key idea here is you take the kind of one block of the diffusion, but you copy it, and then, so the output is the original fixed weights together with the conditioning, but it sort of operates in the same image space. And the zero convolution, I think it's a bit confusing, but what it says, you don't start from the beginning. And initially, at the beginning of the training, it's the standard diffusion, but there's no conditioning. But you gradually, because you zero initialize, you sort of gradually add the conditioning. See, I think the best is to get some intuition what it does. So here at the top is the conditioning, and then there are different generations. So it's kind of, it allows you to control better. It's called control net, the output. If you put edges, it will generate different kind of images with this edge structure. If you condition on the image map, it's a normal map, it allows you to produce different images with different, like following this input. Yeah. So it just allows you to better control what you get there. So that's what we build on, and I think I will maybe show you the. I will try to go faster. So the single image transformation was last year paper. This one is you can generate a whole sequence. So given an input image and instructions of what you want to do, the robot can imagine what the scene should look like if you do these changes. So you can think of it almost like a planner, but a planner which generates images. It doesn't generate actions, it just generates like what it should look like if you, it's a little bit like a world model, because it tells you if I do this, and so you can get the instructions if I want to cook a meal. This is my input photo of my scene. I get from Llama or some language model, I get the steps to cook, I don't know what it is, tortilla chips. And then the model will give you the images, what it should look like when you cook the tortilla chips. Yeah. So it's the reason it is a bit like video model, but the video models currently, they cannot do such complicated things. Yeah. This may take the instruction video to do this maybe have like 10 minutes or sometimes 15 minutes. And getting so long videos is hard. So we are using kind of a video model, but we are not generating continuous video, but only keyframes. So this allows us to benefit from temporal consistency, but still generate like a fairly long action, which would be like so we are only generating maybe 20 frames, but they are over longer time span, but we are kind of missing the information in between for the moment. Of course, the goal is now to also get like the finer grain thing, but it's an intermediate step. And the architecture is an image diffusion model, but it's what we add here is this temporal continuity. So here are temporal attention. So here frame go up, this is the input, and we have additional attention which goes between different frames. And this allows us to make the output temporally consistent, and it's somewhat subtle but interesting. So this is the input image. The previous one, which was doing individual frames, is generating this. So you see here the plane is green, here it's white. But if you generate this temporal conditioning, it sort of maintains the color of the objects across the frame because it's generating them at the same time. Yes?
Do you train it first to generate images and then the temporal consistency? Or?
We use in this. It's an interesting, so the top model is really based on image model. So it has seen a lot of images. This model is actually based on a pre-trained video backbone. And the video backbone has seen much less. So we are seeing Actually, this model is a bit more generalized, is a bit better because it has seen, I think, more stuff than this one. But this one has the temporal consistency. But of what you pre-train is important, of course. Yeah. And but this one is also interesting. So the advantage of having the temporal consistency is that you can actually ask it to do multiple different steps. Yeah? So if you do 2 frames, it does this. If you do 3 frames, it generates also like the intermediate thing. Yeah? So it is, I mean, we don't model the physics of liquids, but still the model is kind of generating intermediate, how this, I mean, it's not of course 3D, but it's sort of generating intermediate steps, how this should look like. It has some problems I'll show you later, but it's, I think it's an interesting, of course, direction. Again, key, yes?
So how do you condition it to do the next step? Is it like you want it to say, I can imagine that if you tell me the next step, it can be far more next step than the one.
Yeah. So it was one of the key things was make variable number of steps. Here, by the way, the steps are given by the language model because we ask it to cook a certain meal and it comes up with 7 steps, sometimes 3 steps. If it's just eggs, boiling eggs, maybe 2, 3 small. If it's something complicated, maybe 20 steps. Yeah. So the number of steps come, but we have to the model, and one of the key things we had to address was how to train the model with variable number of steps, and it was kind of domain randomization. So we are during training we randomize the size of the the number of steps basically. Yeah. So we have to. Sorry. The conditioning is always the input image, single input image, and then you get the sequence of instructions for the different steps, and then that's it. Yeah. And then it generates a consistent output, and there is of course temporal attention across. Yeah. And we are so this is kind of extending an existing video model. I think I forgot now what the name is. Maybe somehow it's not on this slide. I will look it up. So we take existing video model, but fine-tune it on lots of instructional data to do this, like a not temporally, like continuous video, but do this longer steps. Yeah.
So would you be aware of somebody who actually trained the whole model like that? Because you don't need to do it like that. You can just train the decision model that would be conditional only if you do that somewhere.
Which would be...
you could still train the whole model like that. Not just, you don't have to fine-tune it.
From the beginning? Yeah. Well, so current video, now the Google Veo came out there. So I don't know how much one could compare with it. Also, we haven't, I mean, it just came a few days or weeks ago. One could compare with it. So here, it's this has been really trained or fine-tuned to do the instructions. So you observe from 3 to 20 or, instructions from instructional, like how to do something. And it does the images for the instructions. Whether the video model Veo would do it, I don't know. We could try to put the instructions and ask it to generate the video. I will see if it does it. Actually, it's a good experiment which one could try. And I don't know if it, sometimes, but the instructional videos themselves are quite long. So they are often from 5 to 15 minutes. I think the limit is 15 because then I think we discarded the longer one. If it can do 15-minute instructional video, all correctly, I would be impressed. Yeah. So this is it, a lot of it again was in collecting data. So we had a special procedure where we took lots of like instructional videos. We take the narration, use language model, identify this. So take the narration, identify the steps of the procedure from those. Of course, the language model itself knows the procedure, so we know the number of steps. It gets what the task is, and then we use alignment. We find in the video the best frame matching the individual step. We have some way of measuring confidence, and this way we can form a fairly large. I would say there's like hundreds of thousands of examples of sequences like this with the instructions on how to do something. And here are some more results. I think the paper is going to be presented like, I don't know, on Saturday at CVPR. So we are, Yeah, I think maybe what's also interesting is it can do quite, we are happy, we thought it would be hard, it will be impossible or difficult, so we are kind of happy we could do something. Of course, how useful it will be for robotics, time will show. This is interesting, you do quantitative comparison, and these are different models, how one can do it. One should add the VO model from Google to this now, one could add it. What I found particularly interesting is the source sequences. So for a specific input frame, so our model is doing reasonably well to compare to comparison. Stack diffusion is the closest competitor. So this would be, it's a user study. So you ask someone watches the video, the output, the frames, and user asks, do I prefer, it's A/B testing, do I prefer method, our method or stack diffusion? Is randomized, you don't know which method it is. And so people look at it, and there are different dimensions. You can say how the steps are accurate. Is the scene consistency accurate? You ask them one question. Is the task well represented? Someone asked, well, did you try the original video? And we said, oh, it's interesting, or the steps in the original video. And so we also did it. And of course, the original video is better because that was the instruction video we trained from. But it was not that much better. It was like in 42% of the cases, the users actually preferred our generated result. And we were wondering why that is. And it's interesting because in the instructional videos, there are often steps which are not shown. Yeah, so there's like and then you get the chicken from the fridge and put it here. And it's not shown, the chicken from the fridge, because it's assumed you do it. But our model can do it. It can also do the stuff which is not shown in the actual video. Yeah, so it's been always a problem working with instruction video because they talk about stuff which they don't do. But our model does exactly what they talk about. It generates everything they talk about, it generates it. So it was somewhat surprising to see that sometimes people prefer the results of our model better because it had everything which was written in instruction, the model tried to generate. There was no skip steps. And some failure cases, some things are hard. This is an example of like a blowing up a balloon. So it's somehow, it goes to the mode. Typically the training data balloons look like this. It's hard to represent this balloon. I think this one is especially like this one. It says sliced apple, but in the training data, it has not seen sliced apples. It has seen sliced onions. So it sort of slices the apple like an onion, you would do. But so this is examples with which the model, you get things like this if the training data has, if your test setup is not quite matching what you have in training. So this can happen. So basically it's not perfect. Yeah? So these are, you can get things like this, which, and I want to finally, it is actually, I'm going to show an example of our work in a bit more detail, but there are these what's called real world simulators, which are really generative models, which you can condition not only on the input image, but also on the actions, and they will generate what would happen. This was a very nice, it actually was best paper award at iClear last year. Unisim, where, so these are all, part of it may be real data, but the rest of it is generated. So it's actually generating also the motion of the robot, depending on the action. So it's like a different way of doing simulation. You don't simulate physics, but you train the model to generate what the world would look like if you do specific action. And I think I really need to speed up to the last part about the learning from. Any questions, by the way, to learning from simulation? And I'll zoom through learning from other machines. Yes?
I understand that it's useful whatever you presented as a general for everything, but does it help us also for learning in the context of what is present? How would you use it for the machine to learn?
How would I use what the
images?
Yeah. Truth is, we don't know yet. We haven't tried that. But I think these word models, people are now trying to use them as kind of predictors what would happen. Yeah. So It's always a bit tricky because depending on the training data. Often, especially these instructional videos, they don't have failures. That's one of the big problems. So for the robotics, you need to see the failures as well. So I think it's, you know, how, okay, one successful example which I've seen is in Wave, you know, the autonomous driving startup I've talked about earlier. I think they are based on world model. What exactly they do, I don't know. It may be they also use simulated data and then can simulate failures. One problem with the real data often is that you don't see the failures. So, but we don't know exactly what they do.
Does this use audio data as well? Like audio?
Yeah, it's a good point. If it's audio, I don't think they use audio here, but it's a good point. Especially I've heard people mentioning audio in context of the instructional videos because often the sound may give you like more precise localization of the action, like when you put water or like we often struggle to localize things, and we have never done it, but I think it could be a useful cue like for better accurate localization. That's a good point. So people do work also on audio over like video audio models. But I think the robotics guys, they didn't, you know, this beginning. I've seen some actually work on robotics in audio also regarding materials, for example, is that you can sort of help the robot as an additional auditory input. But most of the work, I would say, is focusing on video, visual inputs, language. Touch is beginning, and I think audio a little bit there. Localization I've seen also, I think there is some work, not much, there is some work, yeah. Okay, I'll try to zoom through learning from other machines. This is an example of an early work, but nice work in, they had a bank of robots and they were interacting. This is reinforcement learning. So this was around early, I mean, it's been going for a while, but, and they are kind of, and they had it running for, you know, days and weeks and trying to interact with the environment. When I talk with roboticists, they kind of regard that as not a success. Yeah, so somehow it wasn't, even though they've been running for a while, the robots did not kind of, and this is not my words exactly, is that there was not a breakthrough. And the question is, why is that? I think sort of two reasons, possibly. One of them, you can notice they are all the same. Yeah, so the same robots working with the same objects. So this is just so the scaling. It was not enough variety. And second, I think the reinforcement learning paradigm, where you just have the robot arbitrarily play, is certain limits. Yeah, so you can, you will see later that, you know, what seems to work now is what the community calls offline reinforcement learning, but often it is imitation. So you kind of have teleoperated robot doing things, and you can just learn faster from examples, rather than having to discover something useful. And nevertheless, I think it was a very nice work trying to push the limits of robot scaling. I remember this is at the time where most people had a single robot and they would sort of do the experiment, like, and then, so running a robot over a time was not often. Another example is getting to the teleoperation, yeah, a bit later. This is like a, you know, kids' kitchen environment in the lab. But you see it's not quite visible, but there is like a setup of bimanual, but there is multiple cameras. It's a bit busy scene. And here there are teleoperation, like a virtual reality, like a setup, where you can, the operator can operate the robot. And using that, they can collect data. And this really turned out to be a very important kind of idea. I mean, of course, teleoperation, imitation learning has been going for a while. I don't have all the citations, but, and I will maybe skip this example. And now there is, this is really like a, you know, 2024, like within a year, the community has also begun sharing data. And this is really becoming now interesting, because so far everyone was doing their thing on their robot in the lab, and almost never, like the most generalization was that they would take it to a different room. Yeah. And now the robotics community is beginning to share their data on different robotic platforms and different environments, at least to some extent, even if it's university environments. And so it's called OpenX. There are 22 different embodiments, different robots. they are doing different skills, and often this would look, the data is that you have someone operating the robot, sometimes the robot may be doing also by itself, like running a policy, and there was a language description of the task, like pick up a banana, and the robot would go and do the stuff, and you would have the motion of the robot together with the camera input. And sometimes, but it's sometimes one camera, two cameras, depending on what the lab is doing. So I think it's a nice effort towards at least a little bit of scaling of the data. And I want to show you some examples of work. I really like this work. Mobile Aloha is from Stanford, from the team of Chelsea Finn. And they've created this platform where, this is this PhD student, never underestimate the kind of power of the learning of PhD student. He's operating the robot here. This is like a setup with 2 arms, but you see, I will show later, this is like a remote operation. And this way he can collect data with the robot. So this is the platform, and this is example. So this task is called clean restroom. And note, this is 10 times speed up. Yeah, so what you see here is 10 times, so he's usually doing quite slowly, doing a particular task. He's picking up a towel, paper towel, trying to, take it, then he's using the paper towel to clean the mirror a little bit. And then he's maybe using the sponge to do something. And this way, in this paper, they have, maybe in an order of 10, 20 tasks. And for each of the tasks, the student collects maybe 100 trajectories. But trajectory here would be really like he's recording the video together with the motion of the robot and he would maybe do it 100 times, this task, or 50 times. It depends on different tasks, different times. And but what's interesting is that then the robot can go and do the task itself. At the moment, we are still talking the same environment, the same objects, but the robot, if you record 100 trajectories, I will show you a little bit what type of models they are using, but the robot then can go, and this is now without teleoperation, it can, it can do a fairly complicated action. So this looks very impressive. I thought this is one of the most impressive robotic demonstrations I've seen recently, or like in last, so far. The issue with this particular paper or demonstration, it is not known how much generalization there is, and this is very important. Like, is it, at the moment, what this paper shows is generalization on the level, they move the glass like by 5-10 centimeters, and the robot, if you move it maybe this, the robot may not be able to do it. Or if you replace this bottle, I'm almost sure the robot will not do it. Yeah. So, but still they are able to kind of, I would say, overfit on the specific environment. If you put the robot in a different kitchen, it's, it will probably not do anything or break something. Yeah. But still, it's an interesting that they are able to, and the success rate, by the way, for this is about 60%, I think, for some of it, or roughly. I don't know the details of or 80%. It's like, it would fail in 2 out of the 10 trials. So and now we are going finally to this vision language action models. I think this is the last part which I want to cover. So from the same team, maybe also some other people, there is a startup called Physical Intelligence. And when they saw these type of results where you can actually generate these action, this is, by the way, and we will see that it's kind of a policy. So it's really the robot is learning, given an input image, produce an action. Yeah? So there is no model of the world, no trajectory optimization. It's just sort of producing actions. Yes?
So how was that working with the control? How can I define the task in the environment?
By language. So you tell it cook shrimp, and it will do this.
So
It learns the sequence of the steps for this task. Yeah. And so in that startup, my understanding is but it's great that they are putting the learn models, the weights online. They don't put the data. They try to scale up this data collection procedure, this kind of teleoperation. And I think they claim, or they've collected, I think about 10,000 hours of this type of operation. maybe even now more, and try to achieve a certain level of generalization beyond the specific scene. How successful, we'll see, and what I'll try to quickly explain what they are. I think this is, by the way, this is not just them. There is a lot of work which now in robotics, which is trying to build vision action language models. I'm using this as an example. There is many others, but I think are following similar paradigm or setup. This one is maybe one of the most visible models, and it's publicly available. I will show you, we also use it. And the setup is that you have given language this instruction, you want to drive the robot based on visual input. This is the setup. This is the model. It is it's kind of even so I will first discuss like the different, it's a complicated model and uses different type of training data at different times. Yeah. But basically it's a visual language model, similar to what I've shown you already. So it's a transformer which is processing images and language and outputting language. The difference is that it's not only outputting language, it's actually outputting also tokens which drive the robot. So it's outputting, it can output natural language, but also it can output these tokens which drive the motor, which drive the motors on the robot. And it's trained to do that. There are different, so first of all, there is like internet scale pre-trained vision language model. They use a Google model called, I think, Polygemma. So it uses pre-trained language model, pre-trained vision model, putting it together on kind of internet scale. And then it's interesting, it's adding robot data, it's adding the OpenX embodiment. So these are different robots in different environments. It's not a huge scale. The robotics data is much smaller scale compared to all the other data, but at least it's beginning to grow. And it's fairly coarse. These are different robots in different places. And finally, they do this high-quality post-training when they really train, maybe on a specific environment, on these sort of manually collected high-accuracy actions, typically for the specific embodiment you're going to work with. So this is now fine-tuning on the specific robot you're working with the specific, camera of the viewpoints, with the specific grippers. And I will maybe skip it and go directly. This is kind of explaining to this. Yeah. So this is the model. It's very similar to what I've seen. So input is a video through VIT. So the input, you put the video frames observed from the cameras. If you have 3 cameras, different viewpoints, there will be 3 different viewpoints. This is on 2 cameras on the grippers, one which is kind of overlooking the scene. This is a transformer. This is like a vision language model to what I've seen. So you can put tokens for the input images, tokens for the action which you want the robot to do. And it will process it, it will contextualize it all together. And then there is the action expert. And now it's interesting. There are different, on the action experts, this is the part which is generating that. So it has an input also the current state of the robot. And then it produces the next steps of the robot. And you can either use like so it's an open problem. There's no clear winning solution. Different solutions. You can either, how do you tokenize the robot control? So you can do some quantization. What seems to work reasonably well is to use for the last part diffusion. Yeah. So what's the output of the diffusion? So in images, I will draw this. In images, we were diffusing an image, which was a matrix of pixels in some latent space. Here, the output is a trajectory of the robot over time. So you have also matrix, but over time, and each column is in, if you have 7 degrees of freedom robot, it would have a 7 DOF at different timestamps. So the output here, the AT and AT plus N, where A, this is AT. These are kind of the torques of the robot. And of course, is it position, is it torque, is it velocity? They seem to pre-train with everything, and then you have to fine-tune for your specific case. Yeah, so I think this is like a very much ongoing work, but it's exciting. There'll be lots of research on how to do this well. Diffusion seems to work quite well. So what you generate is several actions in advance, and then you observe again set of images, you generate a set of actions, and the robot can do interesting things. This is the video from the startup which they published, like, I don't know, 2 days ago. And what they are claiming that they pre-trained the model on some data, and then they are taking the robot to a new, they rent a Airbnb in San Francisco, and they are taking the robot to the new Airbnb, an environment which is never seen before. I will maybe go through faster. It's a startup video, so they are maybe a little bit overselling, I don't know, but we need to quantify how the generalization works. But it's quite impressive. The results are impressive. This is Chelsea Finn. She's saying, can you please, I don't know what was the action. She says, put the dishes into the sink, and the robot goes, apparently in an environment which is never seen before, executes by language the task and puts the dishes in the sink. I think then she says to clean up the stain, clean up the spill, and the robot uses the sponge to clean up the spill. So I think to me the main question and problem is generalization. Like how well does, because before, it was really just a placement of the object. So I think at the moment what we are working on, and it seems also other people, is a benchmark which would allow us and the whole community to benchmark the generalization of the robots. Like how well it's going to work on new viewpoint, new environment, new object. Yeah. Yes?
How will you use the time? So it only, the diffusion models only predicts based on, let's say, last step where it was in the condition.
No, so there is a certain time horizon. Like I think it's at the moment, I think it's operating at about 10 hertz or 15 hertz. And it's producing about 15 steps. So it's kind of producing action on a horizon of about 1 second. But you run it more often, you try. Yes? So it's sort of in a window, so it starts executing, you run it again, but the horizon it produces about 1 second.
And so it has some automatic stopping mechanism saying like, now I understand I finished the task. Because
yeah, it's a good question. I don't, I'm not, it has, I mean, at the moment, it's just a language model. So I don't think it is so I'm a bit, and my students, I will show you, we are also now running it. These are, actually we took the model, we downloaded the weights, and we fine-tuned it. The Droid data set is so we have a Panda robot, which is becoming somewhat standard in the university environments. There's certain cameras which have specific viewpoints. It's important, and it has specific gripper also. But if you use different gripper, it may not work. So really the level how well this model works, it's very unknown. Like we have to, the whole community starts to measuring and understanding. But we took and fine-tuned that model on this setup. And because there are other people who use very similar setup, there is actually a reasonable amount of trajectories. Like again, trajectories, the language description, execution of the robot, often by a human. My students also have tried to, we have also teleoperation, so we can also teleoperate it and also fine-tune in our trajectory. But this one is what's called zero shot. So zero shot means it has seen this setup in other labs, but it's for the first time seeing our lab, our robot. And it's running the thing, and it's just a language model, so there is no safety, nothing. So they are always running it with like a hand on the stop button. Because you don't know, it may produce something, it will sort of go, it will hit the table. So I want them now to implement like a safety so that when the robot at least will start hitting the table or like outside of the boundary, it will stop. Yes, so have at least basic safety layer. But how to really do a safe operation of this, it's an open problem. We have some thoughts how potentially we can do it, combine it with control, but it's a very much open area. I will show you our put banana in the box. You type put banana in the box and it just goes, based on these images and executes the action. So it's very different setup. So no pose estimation, no planning, just does it there. If you tell it fold the t-shirt so put banana in the box we could also do without pose estimation, but folding t-shirt it's harder. I think we do, how to do post-estimation. It's a bit dark, it's hard to see, but you will see how the robot struggles. Yeah, he has only one hand, poor guy, so he does something and then it doesn't quite work, so he's then trying to repair it for a while. So like, when does it stop? Yeah, so it just tries and tries and tries, and at some point it stops. Yes.
So I understand that, for example, when you think of the agent systems, in the past you have something that maybe in the prologue would be like series of ways how to perform the task. But I guess that this cannot be like that. It cannot know that I've already failed to do that and now I should try different approach because it has memory. So this can probably never.
Well, it says a little bit of history, but not much. Yeah. So at the moment these are kind of local.
So it has no way to understand I've already failed these 3 ways and maybe I should try it.
At the moment, no. Yes, at the moment, no. But it's very interesting. There are papers appearing like every week. One of those areas which is receiving lots of attention. There's a recent paper which is interesting, which is kind of because these diffusion models, they are kind of comparing it to a nearest neighbor baseline and showing it's performing very similarly. So at the moment, it's different compared images. You have billions of images, but in these trajectories you're operating in thousands, maybe sometimes only hundreds, tens of thousands of trajectories. And the paper is kind of showing that it may be that at the moment we are operating these diffusion models for action generation more in this memorization stage. They are kind of copying the training data, but it is unknown. Yeah? It's open problem, and how well it works and what it exactly does. But it's interesting. And I will show you one failure, and I think I'm almost done. So this is just pour from bottle into the bowl, and maybe it just hasn't seen a bottle like this. It's somewhat, it tries, goes around, and doesn't do it. So. Yeah, I will sort of close. I want to finish. So we will be doing this for a while. We have a European project called ELLIS, which is training. It's a fairly big project, 32 partners, and it's training European open. It's going to be multimodal model. So going to be lots of video language, different things. I am excited about it because it includes very good people from Europe, like Robin Horombach, who did the latent diffusion, is part of the project. So I'm curious what's going to happen. It's addressing the whole circle of the model development, from data collection, pre-training, large scale. They're going to study the scaling aspects and fine-tuning and for specific tasks. We in particular are going to do robotics in this project. So we are going to fine-tune this model for robotic environment. We're going to work with the startups Robotwin, who is doing manufacturing, kind of doing specific tasks in like coating. Yeah. So, but we'll see how that goes. But there are different tasks. Yeah. We are doing the robot perception with Robotwin, but there are others, like you're going to be using media, earth modeling, autonomous driving, but other things. Yeah. So it was a kind of big call with, I think only 2 projects got it, so we are excited what's going to happen. And I want to kind of last maybe 2 minutes. I think the scaling the data, I don't think we quite got it. I think at the moment we are getting these trajectories, we are able to share them between labs, great improvement. But we use all different robots, this is also good. But I think really we're going to see the scale once we start really kind of, and I will show you not sharing data but model parameters. Because we have all these robots which are kind of operating in different environments, they are equipped with visual sensors. So they can potentially capture the large amount of variety of the world. And at the moment we're sharing data, but I think really what will help if we can have these robots which can operate in their own environment, but not having to upload data, but learn their local models for doing different things and be able to share them with each other. Yeah. I don't know if it's going to be single server or shared among all of each other, but I think having the ability to share model parameters will be very important. Yeah, because it will be able to, it's going to be much more efficient. Yeah, and the robots will be interacting, doing their thing, and only when they succeed, they will share it. And if we are on a distributed scale, we can get to the scale we are getting now in the supercomputing centers on language, potentially the robots. But at the moment, we don't know how to do it. We don't know the generalization aspects, even how to share it, how to scale the models to change the number of parameters. So, but I think it's a very interesting area of research. And I think along the way, we're going to have lots of exciting applications. It's going to happen, or it's already beginning happening. This is a farming robot. I think it's a Czech one. We have got robots for specific closed task environments, or in farming, or this is in Rohlík. They have some robots in the logistics. We'll have some successful application and work in the meantime on having long-term autonomous learning, reasoning, planning, interaction. At the moment, all what I've seen is are robots trained from trajectories from humans, doing imitation. The robots are not learning by themselves from the interaction. That's really, it has to stay up. And with this, I want to thank, of course, my team, especially Martin Sedláček helped with preparing some of the slides, Georgi Ponimatkin and Vlado Petrík. It's a team effort. Thank you very much for your attention. Happy to answer any questions. Yes?
Do you think like having some, like all of these robots, many are like just individual, or like in cases where they're just a couple of the same model or whatever, and they're like designed by teams, having like just a standard, like shared unit that has like the same joints and whatever, like having something that is standardized and maybe even mass produced, like would that solve an issue of?
It's a very good point. I think partly yes, sort of practically yes, and we already see it, that actually like what I call the droid setup, this is a specific Panda robot, cameras in a specific setup and a specific gripper. And actually we had everything but not the gripper. We couldn't run it. It just, the data, the pre-trained models didn't work. So we had to buy the specific, and then it started working. So these setups are somewhat platform specific. And also there is not equal amount of data for different platforms. So also the Droid setup has one of the most data, and that's why it's interesting, good to use, and easier to use. So I think there is definitely platform dependence. At the same time, and I think that's also getting a little bit of, I'm going to say philosophical, like how to approach it. I do think that we will need a certain level of robustness for our models to be able to work with different platforms, because the robots, I don't think it will be practical to have one robot for everything. There will be some for home, some for factories. So I think we'll have to have a certain level of adaptability, and the methods will have to work for different platforms. When I talk with Matěj Hoffman, who is doing robotics, especially like humanoid robotics, he thinks, and then I was getting to the philosophical part, he thinks that like embodied intelligence, especially for humans, is very much connected to the embodiment. That it's going to be very difficult to transfer knowledge or representations across different platforms. Yeah, so that like he thinks that our kind of spatial intelligence is very much connected to what we are. If we had like different, embodiment, it would be very different. I'm going to say I don't know. Yeah, I think it may be possible to do some cross-platform learning. I think we are beginning to see hints of that already, especially on the vision component. Because he's coming from robotics, the embodiment, I'm more from the vision background, and I think the vision parts are a bit more transferable. But I think the real answer we'll see. And I think, and what I do believe firmly is that we will only, or not only, but we'll see progress once we are able to benchmark these capabilities in generalization across embodiment, across different, cameras, viewpoints, objects, and only that we'll see what works, what doesn't. So that's what we are putting effort now, is to develop a benchmark so we can start measuring things. Yeah. And that I'm hoping that this will help drive progress forward.
So when we look at this transfer of the parameters of the robots, basically you tackled it in the previous question, but when you have these different sizes, different applications, like going from construction where a robot can have 10 meters to some microcontroller in chip design, like the tasks are very different, the physics is very different, the components are also pretty different. Do you think there will be anything to transfer, or there will be rather some clusters of applications that will be able to transfer any knowledge, but there will be just some brick walls in between.
I think, I think there's probably going to be some clusters, because even in computer vision, we are seeing is that this transfer is helpful, but there is a certain kind of limits to it. So already we see that for often pre-training versus fine-tuning. The better your pre-training task or closer it is to your final target task for fine-tuning, the better. So we always try to design the pre-training tasks so they are close to the fine-tuning. So I think the proximity of the task will matter. At the same time, it feels that especially the task which will require like some world model or understanding how world works, I think this partly could be transferable. Is that if you can learn it or observe lots of instructional videos, and that may help you in other, but of course how far we'll see. Like manufacturing, maybe home could be transferred between each other. How far to autonomous driving, I don't know. But yes.
So in many fields of machine learning, you would really benefit from self-supervised pre-training. So would you also, I understand that in all your things you can partly use it because you use vision model and so on, but would you also believe that there is some connection in pure robotics, and if so, how would it be used somehow to unlevel it?
Yeah. I think it's an excellent point. We have lots of argument with Alyosha Efros about this. I mean, like a positive discussions, let me put it this way. And he rightly points out is that the current, also the work with the imitation learning, there is, I believe, mostly successes in those examples. You don't see much failures. And of course, in general policy, once you get a little bit of the policy, and you may not know what to do, and it may lead to some catastrophic failure. So having, and this is the area where I think self-supervised pre-training can help a lot. Yeah. So Alyosha is talking about having the robots really discover basic skills, and this may help them to really cover better the robotic space, see some failures, but in the end, I think for successful applications, we will need all the components. We will need some self-supervised pre-training, we'll need the learning from simulation, and I think we also need the model sharing. I think sometimes when we discussed it, he compares it, analogy, I don't know if it's perfect or probably not perfect, but how close it is the self-supervised pre-training is maybe like a child, it works, learns how to, so basic operation, like what are the joints, and then when you show it the skills, it's like in the school, you show it like how to do stuff. But when the models, what I think where the true power will come when we start sharing the models across the robots, like from the whole world, then it sort of becomes like sharing the knowledge. But of course, how far it will go, we'll see. Yeah. But I think there is a little bit of, I kind of, to some extent, like this analogy, is that it's important for these different levels of operation. Yeah. But I think, as I said, it's hard to, we don't have systems which would combine both. We have one example system. I think what will now happen, we will start benchmarking, measuring how much this helps, how much doesn't, is this important, do you really need that? I think it's an area, I feel at the moment, but I'm biased there, but I think because I work on this, but I feel this is the area with the physical interaction where it's gonna see a lot of, I think it's gonna, or it's already begin undergoing this transformation which we saw in language. I don't know if in speech you probably also saw it. In vision we also saw it with, I think it's coming to the robotics maybe faster, because we know based on experience what happened in language and vision, and we use those models, but slower because we need to interact with the world, which is slow. So it's hard to predict how fast it will be. Yeah. But it's very exciting to now it's beginning to see all of this.
Yeah. So if not, let's clap and thank
Thank you very much.